Hariharan sir, am I audible?
Yes, sir, you are audible, sir.
Okay, thank you.
Good evening, everybody.
Good evening, sir.
Welcome, sir. Welcome, sir.
Good evening, sir.
Good evening, madam. Guests have joined, madam.
One person joined, sir. One from London is yet to join.
Okay.
Yet to join.
So we welcome Dr. Arun Aloysius, is it? IIT
Yes,
Guwahati.
Yeah.
Good evening, everybody.
Good evening, sir.
He is on mute, sir. He'll be exactly joining at 6. He has joined, actually.
Fine. Thank you.
Oh, hi. I'm here. Yeah, thank you for welcome. Inviting me.
Presentation.
Am I audible?
Yeah.
Yes, sir.
Okay.
All right.
Ma'am is in mute. Ma'am, mute. Ma'am, please unmute, ma'am.
மேம்
Please unmute.
மேம் அன்மியூட் பண்ணுங்க அன்மியூட் அண்ட் ஸ்பீக். சுபத்ரா மேம்.
Yeah, start from the beginning, madam.
Yes. Good evening to all present here, respected dignitaries, esteemed guests, faculty members, and dear participants. I am Dr. Subhadra Murugan, Professor and Head, Department of Electronics Engineering, VLSI Design and Technology of this esteemed institute, RMK College of Engineering and Technology, Tiruvallur. With the blessings of Almighty, as a co-coordinator of this program, on the behalf of ACT, on the behalf of our college management, and on my own behalf, it is my honor to warmly welcome you all to this inaugural session of the AICTE Atal sponsored 6-day online faculty development program on unveiling quantum computing from qubits to quantum algorithms and interdisciplinary engineering perspective. This program is jointly organized by the departments of Electronics Engineering and the Computer Science and Engineering of this college, and it will be held from this evening, December 2nd to December 7th, 2024, from 6 p.m. to 9 p.m. daily. We are delighted to have you join us for this insightful journey into the fascinating world of quantum computing. Today, we gather to commence an remarkable journey of learning, discovery, and innovation in the field of quantum computing. We have an inspiring lineup of speakers and distinguished dignitaries who have joined us to make this occasion special. Without further delay, let us begin the program with a fitting tribute to our culture. To mark the auspicious start of today's event, let us pay our respects to Tamil culture and language by rendering Tamil Thai Valthu. Thank you. To formally welcome this August gathering, I now invite Dr. K. Ramar, the coordinator of this faculty development program, to deliver the welcome address. Dr. K. Ramar serves as the Dean of Research and Professor of Computer Science and Engineering at this institute. He is a visionary leader and an accomplished academician with a remarkable passion for research. A true backbone of this program, Dr. Ramar has played a pivotal role in its planning and execution and ensuring its success. With his dedication and forward-thinking approach, he continues to inspire both students and faculty alike. Please join me in welcoming Dr. K. Ramar to address the gathering. Please, sir.
Am I audible?
Yes, sir.
Yes, sir,
Okay.
yes.
A most respected chairman of our group of institution and respected vice chairman, most respected the chief guest and the resource person of the first session, Dr. Arun, Department of EEE and IIT Guwahati, Assam. The guest of honor, Mr. Shetu Primi, the Chief Technology Officers, Risk Profiler in London, and alumni of our group of institution. Most respected Principal of our college, Dr. Suresh Kumar, Dean Academic, Dr. Sivaram, the participants from Kolkata to Kanyakumari, from various cadres like deans, as professors, associate professors, assistant professors, and research scholars, all part of our country. To deliver the welcome address on the auspicious occasion of the inaugural function of AICT Atal sponsor faculty development program on the topic of unveiling quantum computing from qubits to quantum algorithm and interdisciplinary engineering perspective. My dear faculty members, at this juncture, we have to thank our chairman and vice chairman and AICT authority for giving us permission. I'm very happy to say that there are 9 experts are going to deliver in the 13 sessions on quantum computing for various aspects. And also, we send the brochure through online, and I'm very happy to say that across the country, 7 states are participating in our Atal FTP, including faculty members are participating. So this is a wide scope. The total number of 227 participants are participating in this Atal FTP. With this brief note, let me welcome on behalf of our management and principal and on behalf of our faculty members and student community and by one behalf, let me welcome Dr. Arun from IIT Kaukati, Assam. Thank you very much, sir, for accepting our invitation, being as a resource person, and welcome for this program. And let me welcome Engineer Setu Primi, the Chief Technology Officer from Risk Profiler Inc., London. He is our alumni of our group of institution. Thank you, sir. Thank you very much for accepting our invitation. Welcome, sir. And let me welcome our principal, Dr. N. Suresh Kumar, for his motivations always for the any type of program. I welcome Dr. Suresh Kumar, and I welcome Dr. N. K. Sivaram for his support for this program. Welcome you, sir. And let me welcome the co-coordinator of this program, Dr. Sumatra, Professor and Head of Electronics Engineering, Vlsi Design and Technology of our college. Welcome, madam. And I welcome my team members, Dr. Hariharan, Dr. Uma Maheshwari, Dr. Anish, Dr. Kirtana, and Vidya for their support for organizing this program. I welcome you all. And I welcome the participants from various cadres. I welcome you all in the various positions. I welcome on behalf of entire Rmkcet family, welcome you all for this program. My dear faculty members, attend the program very well and enrich the knowledge in the quantum computing. And also, in order to earn the certificate, you have to maintain minimum 80% attendance. And 70 at the last day of the program, we will be organizing a test. You have to score minimum 70% of the mark, and you have to give your feedback or attendance every session. The link will be given, and you have to give your attendance and feedback for the particular session. So with these few words, I once again welcome you all for this program. Thanks for giving opportunity for the organizers for giving me the chance to welcome the gathering. Thank you, one and all.
Thank you so much for your inspiring words, sir. Next, to provide a deeper understanding of the purpose and objectives of this FDP, I'll take this opportunity as a co-coordinator to share the details about the FDP. Over the next 6 days, we will explore the fascinating world of quantum computing with a focus of both theoretical foundations, practical aspects, in terms of real world applications. Quantum computing is more than just a buzzword. It is a transformative technology that promises to revolutionize fields like cryptography, artificial intelligence, and optimization. Unlike classical computers, where we use bits to process information, quantum computers use qubits, which can exist in multiple states at once, thanks to the principles of superposition and entanglement. This enables quantum computers to solve problems much faster than the classical systems. So what we expect on the 6 days is that from 6 o'clock to 9 o'clock, you'll be having 2 sessions taken by 9 experts from India as well as abroad, from academic as well as from industry. And the schedule has been already been shared among the participants. So this 6-day FDP will cover a range of topics in quantum computing, starting with an introduction to quantum principles, cryptography, followed by the sessions on quantum hardware, quantum programming, and quantum machine learning. In the later days, we will divide the algorithm session in terms of health monitoring, photon statistics, quantum circuits, featuring expert speakers from, as I mentioned before, from the academic as well as from the industry in India as well as abroad, one from Australia and another from London. And regarding the participants that we've been enrolled, we're very happy to tell that totally 227 participants have been registered across the country, representing 6 states, including Tamil Nadu, Andhra Pradesh, Karnataka, Maharashtra, Telangana, Puducherry, West Bengal. In addition, from Tamil Nadu itself, overall 20 districts have been participating in this workshop. And the main mentioning about the certification criteria is that the attendance should be 80% for all the sessions. Once again, I repeat, please make sure that your attendance is 80% for all the sessions that you are attending. And you need to secure 70% of the assessment to receive the certificate. So this is the mandatory criteria that has been given by AICTE for conducting this Atal online FDP program. So we will be conducting an online test. It will be a multiple question objective test on the final day after completing the 13 sessions. And a Google form will be shared for the attendance to all the participants during the session, one for especially for the first session and another for the second session. So you can expect the registration form for the attendance being circulated on the last half an hour of the session. So I request all the participants to enroll the attendance daily for both the sessions, for the first as well as the second. And there will be an individual feedback need to be provided to ensure that you are attending the entire session, so that you need to give the feedback form, then only you can submit the form. And after completing the 13 sessions, you will be given an overall feedback form along with the test. So we would like to extend our heartfelt thanks to AICTE for sponsoring this program. And I like to personally thank my organizing team members and expert speakers who have generously contributed their time and knowledge. A special thank to you all participants for your enthusiasm and commitment to enhancing the understanding of quantum computing. So one thing I would like to emphasize is that please try to ask much more possible questions in the sessions, and use the chat efficiently. Thank you. Moving forward, it is a great privilege to invite our esteemed principal, Dr. N. Suresh Kumar, to deliver the presidential address. Dr. N. Suresh Kumar is not just a dynamic leader and exceptional academician, but also someone I hold in high regard as my teacher and mentor. Starting from teaching me the fundamentals of electronics to guiding the institution with his visionary leadership, he has been a source of inspiration to me and many others. Known for his ability to encourage, motivate, and get things done with efficiency, he exemplifies dedication and excellence in every role that he takes. It is an honor to invite him to share his thought with us. Please, sir.
On behalf of the college management, our chairman, vice chairman, management board members, advisors, or deans. Extend my good evening to one and all present in this program. I welcome you all to this AICTE Atal sponsored 6-day online faculty development program, FDP, on unveiling quantum computing for qubits to quantum algorithms, an interdisciplinary engineering perspective, organized by the Departments of Electronics Engineering with specialization in Vlsi design and technology and computer science and engineering at RMK College of Engineering and Technology, Tiruvallur from today, that is 2nd December to 7th December 2024. On behalf of the management, I extend my regards to the guest, Dr. Arun B. Aloysius from IIT Guwahati, and our proud alumnus, Engineer Sedu Parimi, CTO, Risk Profiler Incorporated, London, UK, for this program. And quantum computing represents the forefront of technological innovation with the potential to solve problems that classical computing cannot address effectively. As educators, researchers, and practitioners, we stand at the threshold of a computing revolution that will profoundly impact diverse fields such as cryptography, artificial intelligence, and big data analytics. Through this FDP, we aim to equip all the 227 participants from Kolkata to Kanyakumari, covering 7 states, with the knowledge and the tools necessary to growth. At RMK College of Engineering and Technology, we have always prioritized excellence in education, research, and innovation. This FDP exemplifies our commitment to nurturing faculty expertise in emerging technologies and creating a collaborative learning environment where ideas and solutions thrive. This FDP would not have been possible without the support of several key contributors, AICTE and the Atal Academy, for sponsoring this program and recognizing the importance of such initiatives. The dedicated efforts of our organizing departments, the Department of Electronics Engineering with specialization in VLSI design and technology, and the Department of Computer Science and Engineering, in meticulously planning, generously agree to share their time, expertise, and insights. And finally, our participants whose enthusiasm and dedication are the cornerstone of this program's success. Dear participants, this program is not just about learning, it's about exploring, questioning, and innovating. I urge you to take full advantage of this opportunity to delve into the intricacies of quantum computing. The knowledge and professional growth, but also empower you to inspire your students and peers. In conclusion, I wish you all a highly productive and enriching learning experience over the next 6 days. May this FDP serve as a catalyst for collaboration, exploration, and groundbreaking contributions in the field of quantum computing. Thank you.
Thank you, sir. Thank you for your inspiring words and your supportive for this initiative. Next, I invite Dr. K. Shivaram, Dean of Academics,
To VLSI Design and Technology, and the Dean Academics, Dr. K. Shivaram, for making this FDP into a reality. Subhadra, madam?
Can I continue, sir?
Yeah, you
Yeah.
please.
Yeah. Next, I invite Dr. K. Shivaram, Dean of Academics at RMK College of Engineering Technology, to deliver the felicitation address. Dr. Shivaram is a man of valor and vision, whose guidance and support inspire us in every possible way. A leader with remarkable forethought, he consistently worked towards the fostering academic excellence and innovation within the institution. It's a privilege to have him with us to share his thoughts and felicitations. Please, sir.
மேடம்
Sir,
சிவராம் சார் ஜாயின் பண்ணிட்டாரா? நாட் எட் நினைக்கிறேன். மேடம்
sir, okay. It's okay, sir.
ஸோ introduce the guest and invite.
Yes, sure, sir, sure. So it's now time for most awaited part of the program, the inaugural address. We are honored to have with us Dr. Arun B. Aloysius, Professor at Department of EEE, IIT Guwahati, Assam, as the chief guest for today. Dr. B. Arun Aloysius is a highly accomplished and dynamic researcher in the field of quantum computing and communications. He earned his BE degree in electronics and communication engineering from Anna University, Chennai in the year 2009, followed by a MTech degree in National Institute of Technology, Calicut. He completed his PhD in electrical engineering from prestigious IIT Madras, Chennai. After that, he served as a postdoctoral research associate at Duke University, USA, where he contributed to cutting-edge advancement in quantum research. He also collaborated with quantum technologies as an independent contractor, gaining valuable industry experience. Currently, he is an assistant professor at Indian Institute of Technology, Guwahati, where he continues to inspire students and peers with his innovative work. I warmly welcome you, sir. And I would like you to take this session forward by delivering an inaugural address. Please, sir.
Thank you, madam, and thank you for the organizing committee for inviting me to this program. I'm audible, right?
Yes,
Yeah,
you are
yeah.
audible, sir. Yeah.
Okay, so compared to the audience here, I am kind of a kid here. Like, so I am very young. It seems like, so compared to the presence of dean and important people of the institute. So I will try to give my opinion on. So why should we learn quantum computing? So one of the important reasons, like it's not about quantum computing, it's more about most of the topics. So I will focus on quantum computing. So whenever my students join, so the first question they ask is why should they learn quantum computing? So what is the use of quantum computing? And the simple and the simple answer that I give, it is interesting for me. So so long back I started learning cycle. So when I start learning cycle, I didn't thought of like whether I will get a job out of this cycling or will I get something out of this cycling. Only thing I learned cycle is like it is interesting for me. So that is where the focus is on. So so I think the motivation for learning quantum computing should come from the point that it is an interesting field. Like so we have this the properties like superposition. How is this superposition happen? That's an interesting question. Like so classically we never see this information as a superposition information. But in quantum sense, we see information how this qubit takes all the values at the same time. Like, so is it possible? Is it really possible? Like our normal intuition, whether it works, like so through our normal intuition says that you cannot have all the possible values at the same time. But it's kind of a counterintuitive notion. And but when you look into the math of it, like so I am a more a mathematical guy, like more analytical guy. Like so I look things from the mathematics perspective. On seeing the math of this, it looks more possible and it looks more interesting too. Like in the first talk, I will try to give an intuition of this quantum qubits. So in that, I will talk more about it, and so that is why that's where we should focus on. Like so, it is more interesting. So more than the job perspective or more than getting projects done or something other than that. So we should focus more on creating interest on this field. So as teachers here, I request everyone to create interest on this field so that the kids, the students, they will learn in future. Once they get interest on it, they will start learning it, and once they learn it, they will get job for sure. Like the job market will grow for sure, and they will get it. Like so, once they learn it with interest, they will develop their skills. And so how to create interest, and that is where we have to focus more on the basics. Like so sometimes people who are interested in quantum computing, like they miss out the basics. Like so what is a qubit? That's a basic question that one can ask. But so when we start research, we may not think about this question. Like, so we may not think about, we ignore this question and we directly go into this, the applications of quantum computing and try to work on it. But what I see is to create interest in the younger people. Like it's more important to start with the understanding of qubits, like understanding of the elementary things of quantum information. That I used to. So once we focus on it, like, and the students get the interest on it, and things go on, move forward, and and it's not only a job creating field, like it's more about skill development. So I focus more on skill development. So the students who quantum computing, the basics of quantum computing in depth, they can apply the same tools or whatever skills that they develop, they can apply it in the other fields too. And I think that is more important than anything else. Like, so they should get this ideas of this basic tools. Like, so normally this job markets, what they see is whether the candidate is capable of using the tools, like more than whether they know the tools. They have to be, they should have the capability of learning the new tools and using it. So they can get that capability only by learning more and more basics. Like their brains can get trained on learning more and more basics. Their brain will get trained so that they can learn more and more further. So that is what I feel we have to focus on, like on when we try to teach quantum computing or most of the other topics. So yeah, with this I thank for this opportunity. Like, and I conclude my talk with this.
Thank you, Arun sir, for your profound insights and for gracing this occasion with your presence. Thank you so much for accepting our invitation and to be the first resource person. Though you are mentioning as you are the youngest one, we feel that quantum computing is being done by the younger people widely throughout the world. So on this occasion, especially I welcome you. And thank you so much for inaugurating this event. Thank you so much, sir.
Thank you.
To further enrich this event, we have the privilege of hearing a special address from our privileged and profound alumni, Engineer Sethu Parimi, Chief Technical Officer, Risk Profiler Inc., London, UK. Sethu Parimi is a highly accomplished cybersecurity researcher and an entrepreneur with a strong academic background, holding a bachelor's degree from RMK Group of Institution, a master's degree from USA, and the most reputed global talent visa holder in the United Kingdom. With over a decade of expertise in cloud and application security, vulnerability management, and cybersecurity program development, he has significantly contributed to global corporations, including Amazon Web Services. His work has been instrumental in strengthening organizational defenses and guiding multi-cloud enterprises in critical sectors such as the government and BFSI. Currently, he leads riskprofiler.io, a web top VC-backed US-based cybersecurity startup specializing in the external threat exposure management. At riskprofiler.io, he focuses on developing innovative solutions to address complex security challenges. His efforts have earned recognition for identifying critical vulnerabilities in leading organizations and for co-developing Cloud Frontier, an open-source cloud security tool. As an active contributor to the cybersecurity community, he is a published researcher, keynote speaker, and dedicated mentor. His work has been featured at renowned global cybersecurity events like DEF CON USA, Black Hat USA, and B-Sites. Additionally, Sethu has authored influential research on IoT security and advanced mitigation strategies while mentoring aspiring cybersecurity professionals to help shape the next generation of security leaders. I now invite our proud alumni, Mr. Parimi, to share his thoughts. Please.
Thanks a lot, Subhadra. Good evening, everyone, and it's really nice having me here. And I'd like to thank all the staff who is organizing this event. And it's always proud to be back at the same college where we both of us. So a quick intro. So myself, I'm Setu Parimi, and I'm here as not even kid, because Arun, who spoke before me, he was mentioning that he was a kid. All you folks, if Arun is the kid, you can consider me as a 3-month baby inside the mother's womb. So I am still immature, but in terms of industry experience, I have been doing cybersecurity throughout my career, even since college days. Since I think it's the first year or second year of my engineering college at the RMK group of institutions. I have started doing cybersecurity, a lot of bug bounty and hacking big applications, and then reporting them, and then getting the pocket money side of things from them. And it was always the curious thing for me, right? When in the first year we have this M1 subject, M1, M2, M3, all these amazing subjects. At that point of time, I didn't know what was the value of studying mathematics in a computer science degree. And later, when I was doing some advanced cybersecurity by myself, learning all these things, all this reverse engineering, all these things had mathematics at the core. The encryption had the mathematics at the core. Cryptography is all mathematics. It's a black magic to me, even till date. So it's always amazing to share the experiences that I've learned throughout the career back with the amazing folks who have taught me all these things when I was a student at RMK group of institutions. And it was a very good topic, the quantum computing. Why quantum computing? Because that's the future, right? Today, the encryption and all these things are relying on mathematics. And tomorrow, the way how encryption, all these things are the reason why we are able to securely communicate with each other on the internet. And if the encryption can be broken, it can be broken with the help of quantum computing. And if that happens, there is no privacy on the internet. And that is the reason why, according to me, quantum computing is very, very important. And we do a lot of, in my startup, we do a lot of threat intelligence kind of things, which is more around gathering all these hacked passwords or breached passwords in the form of hashes. And we use quantum computing in my startup at Risk Profiler to go ahead and decrypt all that stuff and notify our customers that your organization's employees' passwords are breached in dark web, so you guys have to fix it. So that's when we have been using quantum computing in production workloads in for the past couple of years. And before that, I was working at AWS. Even at AWS, it's a huge public service cloud provider, and even they fear a lot in terms of how this encryption standards that they have to protect their customers in transit and also in rest can be defeated by quantum computing. So it's an amazing topic, and I would love to have an amazing insights discussion. So I'll be talking after Arun. So Arun will be covering the next basics around quantum computing, and then I'll be talking about how quantum computing is going to be impacting the cybersecurity space across the globe in real time. So looking forward for all these amazing conversations, and thank you so much once again for having me today.
Thank you so much, Mr. Arun Pirmi, for your valuable words. And hope it's your lunchtime now in London. And hope to see you in your second session. And thanks for being here. And
Thank you.
yeah, I would like to request the committee team. Is Shivaram sir back? Is he joined? Hariharan sir?
Dr. Sivaram sir is not joining, madam.
Okay, okay, sir.
Uh,
Okay, sir. So as a closing remark, I would say so this comes the conclusion of the inaugural session. I extend my heartfelt thanks to all our speakers, dignitaries, and the participants for making this event a memorable one. Before conclude, I wish to again emphasize on the certification criteria that has been imposed by Atal FDP. You need to have 80% of attendance. So that try to attend all the sessions. There are totally 13 sessions. Today alone, the time will be up to 9:30. From tomorrow onwards, it will be from 6 to 9. And I wish everybody to secure more than 70% in the assessment to receive the certification of completion. Per session, you will be receiving an registration Google form that I request everyone to submit it. It will be having an session feedback as well. So we now look forward to the technical sessions that will follow. Let us make the most of this opportunity to learn and collaborate. Thank you all. Have a great day ahead. And I wish to give the handover this to Dr. Arun from IIT Guwahati. Please, sir.
Thank you. Thank you. Can I share my screen?
Yeah, you
Yeah,
can.
you can share.
You can share now, sir.
Okay. Okay.
Can increase a font size little bit, sir, like if possible.
Okay. So that is not possible. Like, so I thought it's a computer, so it should
No
be
problem, sir.
visible.
You
No,
can.
no problem, sir.
No
No
problem,
problem.
sir.
No problem. We can continue.
So, is it visible? Like,
Yes,
Yeah,
it is
visible, sir.
visible.
Visible,
It
sir.
is visible only.
okay, fine. Okay. Yeah. So thank you all, and so welcome to my first talk. This is about introducing this quantum computing. So more than introducing quantum computing, I see this talk as introducing quantum information to everyone. And yeah, remember this quote throughout my talk. So you can ask questions. Feel free to ask questions whenever so you have like so whenever you are troubled. Okay. And so I will start. So in this talk, I will try to answer these 4 questions in this talk. So first is, so how can we visualize quantum information through classical sense? So most of us, I believe, are working on a classical information. We know how classical information looks like and the classical computing looks like. And now suddenly we have to think about quantum information. So the first thing is we have to visualize quantum information through some sense. So I will try to give a visualization. Like I'm trying to experiment on a visualization approach, like so through a coin toss experiment and a modification of the coin toss experiment. And I will try to make you visualize quantum information. And then I will try to explain the importance of quantum information, why it is so attractive for many, like so why people talk about quantum information everywhere. And it is mainly of three important properties of quantum information, which are called no cloning, entanglement, and superposition, which we will talk about it along the lines. And once so and in between this talk, I will again discuss about how to model this quantum information, how we mathematically see this quantum information. So when we think about classical information, we know how to model the classical information. It is just bits. So we say 0, bit 0, and bit 1, or vectors. Vectors are binary numbers or vectors, however we wish, we see those in that form. But then how will you visualize this? How will you model this quantum information in a math form so that we can work and develop more and more algorithms? So that is what I will focus on. And finally, I will just give an introduction to quantum information. I will say what a quantum information is. Since no one is, so I believe in the talk, no one is focusing on this information perspective, like mostly communication people work on information. So I will try to give you how to visualize this, how to quantify this quantum information, and how to see this quantum information from this from a math perspective. So that is what we will discuss in this talk. Okay. And if you have questions, just feel free to interrupt me. Okay. Thank you. So now let us start the first part. The first part is more about visualizing quantum information. So here, let us. So we all know a coin toss experiment. Like, so I hope most of you know a coin toss experiment. So some guy comes and tosses a coin, and we may get either heads or tails. So we can see either heads or tails, and then we put information on heads and tails differently. Like, so either we put we call heads as 0 and tails as 1, or tails as 0 and heads as 1. Now we map the heads and tails into a binary information. So we are, whenever we think about a classical information, we can think of a coin toss or a coin. Like, so there are two sides of the coin. We can share the information in the form of heads or tails. Okay. And for this, we need for the coin toss, we need some important thing. Like, so we toss the coin and we place the coin on some plane. And I call that plane as reference plane for throughout this talk. Okay. So throughout this talk, I introduce a few terminologies that I will introduce along the lines. Okay. So we call this the plane as reference plane, and this is the plane over which my coin lies. So I place my coin over in this plane, and for someone from the above, they see the coin and they can see whether it is heads or tails. And now I just add an alternative, add an additional definition to my coin toss experiment, and I allow my coin to stand. Like my coin will not just lie down. My coin can stand in any angle. Like it can stand. It can stand it at an angle theta, and it can rotate at different positions. Okay, forget about gravity here. So it stands. Okay, and now what I will do is I will call something as an observation sphere. So you can see here. So you can see my pointer, right? Can you see my pointer?
Yes, sir. Yes, we can see the pointer. Yeah.
Okay. So you can see this observation sphere. And what I will do is I will ask some observer, a third party, you assume some third party, an observer. I will ask him to go and sit in a random position here, random point on the sphere, and see the coin and tell me whether it is heads or tails. And now what happens is he can, depending on the position on the observation sphere. Okay, when I introduce observation sphere, I wanted to mention this observation plane too. Along with that, this sphere, this plane that comes along with the observation sphere is called observation plane. Okay, in this talk. And now when I ask a random observer to see the coin from the at some point, and he goes and picks a point uniformly, like everyone knows what an uniform distribution is like. So it's like he chooses every point with an equal chance, like, and he picks a single point on this particular sphere, and he sees the coin, and he tells me whether it is heads or tails. And the probability of me receiving that heads can depend on the angle of the coin, angle at which the coin lies. For example, if you see this first picture, the coin is, excuse me, 1 minute. So if you see the first picture, the coin is tilted like this. Okay. So, which means, I couldn't write here. So yeah, okay, I couldn't write here. Sorry for that. So the first coin, if you see this first coin, so if the observer randomly, when he picks the random point, if he picks this area, the green area, so he will see the green side of the coin. And if he sees the yellow area, he will see the yellow side of the coin. That is the whole point. And now, since the observer chooses the point uniformly at random, it's 50% chance that he will see head and 50% chance that he will see tails. And if my coin is something tilted along this line, then the probability differs. The chance of seeing heads and chance of seeing tails is slightly different. And in classical sense, how can we model this particular information is like you just define a vector in which the first element represents the probability of heads and the second element represents the probability of tails. Or in other words, the first element represents the probability of green side and second element represents the probability of yellow side. That is a standard way in which we represent the randomness in classical when we define classical algorithms. But now, since these numbers are positive, I'm going to tweak it a little bit. Instead of just p and 1 minus p, what I will do is I will do square root of p and square root of 1 minus p. Now, since p is positive, it conveys the message whatever I am supposed to see. But for reasons to give an intuition on quantum information, I wanted to make it as root p and root of 1 minus p. So that is the only change I wanted to do. So now what we have done is from classical bit, we have moved to classically random bit. Okay. And now from random bit, I wanted to move to quantum bit. But before that, in randomness, then there is another interesting factor. So there are different positions of the coin, which gives the same random vector, the same randomness. Okay. For example, you can see this picture, the coin tilted in this way and tilted in this way and tilted in front. So all these three will give you the same values of p and 1 minus p. Okay. So it will give the same vector. The vector representation of the coin will remain the same for all these three positions. And not only three, there are many positions in terms of classical randomness. Okay. Now what I will do is I will define something called as conditional randomness. So conditional randomness is nothing that someone sees the coin, like, so suppose for example, my coin is tilted like this and someone from yellow side, he sees the coin. So he will see yellow, right? So, and now for whoever knows probability well, like we need not go into in depth of the probability, but just for a vague definition, like the randomness of x given x equal to a, it becomes deterministic. Everyone know if I say that x is equal to a, and someone asked me what is the randomness of X or what is the distribution of X. X is purely deterministic. That we know that well. So a similar, so I am trying to translate the same thing into this coin toss perspective. So I keep the coin, and for example, someone from the observer sees the coin from the yellow side, then which means after that, whatever observer I ask them, if they see the coin, they should see the yellow. That is what this means, right? Deterministic means they have to see the same coin again, the same side again. So I model that in this coin toss picture as pushing the coin along those lines. So for example, here if the guy sees yellow, if the observer sees yellow, he or she will push the coin towards the observation plane. And this is the observation plane. And they push it towards the observation plane so that anyone else who is viewing from the same observation sphere, they will see yellow. So if, in this picture, if anyone sees that coin, they will see it as yellow. And suppose if he sees from the green side, assume that he is pushing, the observer pushes the coin towards the green side and pull it over this observation plane. And after that, anyone who sees that coin, they will see only this green side of the coin. Okay, so this one I call it as post observation randomness. So once you observe it, you see deterministic value in classical information, and this is the key point. Okay, and now let us go to the qubit. So when I go to qubit, so now from classical bit, so from classical deterministic bit to classical random bit, I allowed the coin from the surface to, I allowed the coin to stand. Now I will, to move from random qubit to qubit, random bit to qubit, I allow the observation sphere also to move along with its observation plane. Okay. So for example, if you see this coin, now my observation sphere is like this in the figure, the first figure. So throughout the talk, I assume that you can see my pointer. If you cannot see my pointer, let me know. Okay, I can do some other way to be sure, make sure you see this whatever I am pointing out. So here, if you see the first figure, so the randomness is different. Like, so the probability of getting heads and tails is different. Now I can change. So in quantum, in qubit, quantum coin, so I can tilt the observation sphere along with the observation plane. So I can move it like this. And now if you see, the probability of getting heads and probability of getting tails are different. And the interesting fact is, like, if you tilt the observation sphere at a specific angle, you can see deterministic values there. Though it has, so in the standard picture, you have both heads and tails. But in this picture, when you tilt the observation sphere slightly, you can see only yellow side. Okay, so which means the distribution, the chance of seeing different coins, it changes with respect to the measurement plane. Now, if you keenly observe this, now classically we saw that these three scenarios are equivalent. Like, so earlier we have seen that these three scenarios give same the measurement distribution. Like, so if you recall here, so these three kind of positions will give us the same kind of randomness. That's what we have seen in classical sense. But now the difference is these three positions will not give the same probability distribution, because once we change the observation plane, in this observation plane, they are not, this observation sphere, they are not the same. The distribution differs. You can see that now here in this picture, chance of getting green is higher. Oh, sorry. So here's a slight mistake. I think this yellow should come on the top. So here the chance of getting yellow is higher. Like, so the whole point is the distribution changes as we change the observation sphere. Okay, and that is the key point. Like, so now we have to represent this in a mathematical form. That is why we are going to move further. And the next thing is, I wanted to map this particular so all these things, like, so the rotation of coin, rotation of observation plane, I wanted to map both of them in some mathematical notation. That is where we bring in this classical vector notation, in which you represent the state by alpha and beta, and you have so here we have magnitude of alpha square plus magnitude of beta square. So here we are supposed to have 2 here. Okay, so we have magnitude of alpha square plus magnitude of beta square equal to 1. Just like classically we had p plus 1 minus p equal to 1 here. So in this vector form. In a similar notation, we use the same thing. You have alpha and beta with the magnitude of alpha square plus magnitude of beta square equal to 1. But in classical sense, our alpha and beta will take real values. And in quantum sense, our alpha and beta can be any value. It can be real or complex. It's not any value. It can be real or complex values with satisfying this condition: magnitude of alpha square plus magnitude of beta square equal to 1. Okay. And that is that's the step from classical random bit to quantum qubit. Okay. And now, so we can think about, now we should think about what happens once you measure the quantum state. So now suppose you measure the quantum state again. So what happens here? So classically it gets pushed to one of the state that we have seen here. So if you see this, so if you try to see this, measure this particular classical state, you will get heads with the probability p and tails with the probability 1 minus p. That's what we have seen earlier. And similarly, the same picturization in quantum sense. So if you try to measure this quantum state, the state represented by alpha and beta, if you try to measure it, and this particular state will be like, the resultant will be like, either you will get the state 1 0 with probability magnitude of alpha square, or 0 1 with the probability of beta square. So that is how we can intuitively think about this quantum information. And you can see some of interesting quantum states, and this is one of the interesting quantum states. And this particular, so if I make this 1 0 as 0, and again I miss out something here. So if I try to make this this 1 0 as get 0 and this 1 as 1. So classically this is the bit 0. In classical sense, this is bit 0, and classical sense, this is bit 1. But in quantum sense, in classical sense, the deterministic values are 1 0 or 0 1. But in quantum sense, we have different values. A qubit can take any of these values like alpha and beta. So we have multiple values. So our quantum state will be like alpha times 0 plus beta times 1. This is what we call it as quantum superposition. So it can take values. So at the same time, our qubit can be take ket 0 and ket 1. But here ket 0 and ket 1 means that both are classical states. So the quantum superposition, it actually states that it's a superposition of two classical states. Okay. So when you think about quantum state, it is a single state. The state of the quantum system will be alpha and beta. So this particular, it can be represented by this vector. That state is single state. That is not a, so to be specific, that is not a superposition of a quantum states. It's a superposition of two classical states. And we encode information in classical states and get this advantage of the superposition, which we will talk about soon. Okay. And these are some of this vector notation based on the positions of this coin. So we call this particular position as plus state, which is which can be represented. So when you go through this quantum vectors, we will see this notation, and this represents this quantum state 1 by root 2 and 1 by root 2. So this one, and this one represents the vector 1 by root 2 and minus 1 by root 2. So these are the two different vectors. Okay. And now throughout here, we assume the standard plane. So now if you see this, if I try to measure this coin in the standard measurement plane, it is heads with, you will get 0 with the probability p, and you will get 1 with the probability 1 minus p. Or here p equal to 1 by 2. And 1 minus p remains 1 by 2. And if you try to measure this minus state also, so you will get the same statistics. So it's 0 with the probability 1 by 2 and 1 with the probability minus 1 by 2. And now suppose I move to, and there are other cases, like if you see this state, so the coin, so this vector is represented as 1 by root 2, and this is I times 1 by root. And now still, if you see this conditions are satisfied. But remember, this is not same as 1 by root 2 and 1 by root 2. This is, these two states are two different states. But with respect to this measurement basis, when your measurement plane is this plane, when your measurement plane is this plane, then these two are equivalent from an observer's perspective. So when someone trying to look into the quantum qubit, he will see 0 with the probability 1 by 2 and 1 with the probability 1 by 2 when the observation plane is like this. Okay. And these are some interesting orthogonal states, which we call it as plus and so we call it as plus I and minus I, and this one we call it as plus, and this one we call it as minus, whatever we have discussed here. And this is 0 and 1. These are some standard basis that people try to understand in various textbooks. When we try to understand the elementary, when we try to go for an elementary understanding of qubits, we have to understand what these vectors are. So someone who know linear algebra well, they can point out that these forms a basis. Like, so this is one basis of a two-dimensional vector space, and this is another basis for a two-dimensional vector space, and this is another basis for the two-dimensional vector space, which we call it a standard basis. So for this talk, we will try to keep those terminologies away from our. Okay. So once we represent this quantum vectors through quantum state, like using a two-dimensional vectors, and the next goal for us is to see what to do on this quantum state. We know we have defined quantum state. Now we have to do operations on it. Once we know how to represent an information, the next target will be how to perform operations on that information. Okay, and that will be the next task. So what are the operations that we can do on a quantum information? And these are some of the interesting operations which we can do it on a vector. Like, so this is nothing but you represent a quantum vector like alpha, beta, and what you can do is you can do a Pauli x. X is something like 0, 1, 1, 0, and the resultant will be beta alpha. So what does it do? Like, so so what does it do? X translate the state 0 to state 1, and it translates state 1 to state 0. And this particular operation is called as bit flip operator in the literature. And this is equivalent to, this is same as the classical bit flip. So this is a classical operation too. So classically, this is valid, rightly valid. Okay. And if you see the second operator V, which is actually translates 0 to 0, it do not do anything for 0, but it changes the state 1 to -1, or in other words, it changes the state alpha beta to alpha minus beta, which means it is adding a phase angle to the state, the coefficient corresponding to state 1. So we normally call this operator as phase flip operator. Okay, or in other words, in some literatures they represent this as sigma x, sigma c, and sigma y. And sigma y is Pauli y operator, which is another operator, a combination of. So sigma y is, so if I recall right, sigma y is, this y operator is equivalent to I times x. Okay, and the thing is, like, this C operator is nothing, it cannot be done in a classical computer. So we don't have a C operator in a classical computer because our classical information are always like, it takes a value alpha beta, where alpha and beta are always positive. If you think about the classical information, classical randomness. But quantum information, we have the freedom, like your alpha and beta can be anything, any complex number. So we can tilt alpha and beta according to our wish. So our C is something like, it translates alpha beta to alpha minus beta, which is allowed in quantum computing. In classical information, this kind of operation is not allowed. That is the whole point. So, and yeah, so, and other operators that we can do on quantum information is something called as rotation operators, and which we can tilt, we rotate the operator. For example, your qubit is, if your coin is placed like this, you can tilt the coin in a different angle with the same, with the, for example, in this case, it is with this axis, with the C axis. So since it is with C axis, we call that as RZ rotation, and we can rotate it in every direction, RZ, Rx, and RY. And we, and the interesting fact is, like, so this RZ is more experimentally feasible. So people mostly try to look into this RZ rotation, and mostly this noises and more important transformations that can be done experimentally are mostly RZ translations. Okay, and on the other side, along with this, so whatever we have seen is as operators on single qubits. So I take a bit, I translate to 1, it is equivalent to your C0 gate, and then you take a bit, you keep it as such, or you add a phase flip. So you add a phase flip to it, and this is not a classical gate. This is, so we can make it something different, some a phase flip kind of gate. And then now we need to see the versions of AND gate and OR gate. So we don't have a proper versions of AND and OR gate, but instead we have a version called C0 gate. which is like a controlled NOT gate. This is a standard representation of this. And we use this representation because all the quantum operations in a controlled environment. So if my environment is protected, so if no external environment interacts with my quantum information, and if my environment is well protected, then all my quantum informations are unitary operators, which means all my quantum informations are invertible operators. And to make it invertible, a normal 2-qubit gate, suppose I give an AND gate like this, and this 2-bit gate is not invertible. If given this result, you cannot find what are these inputs. So deterministically. So it's not invertible here. But quantum operations are always invertible under a controlled manner when it is done in a controlled environment. Okay. So we wanted this operation to be invertible. So for that purpose, we will use something like this. And this is nothing but you send the state X and you send the state Y. The resultant will be X as such, and this will be X plus Y. And this is like in binary case, it is exclusive. This is XOR gate in terms of binary, classical binary gates. Okay. So you can think of this C0 gate as a quantum manifestation of an exclusive OR gate. And there are other 2-qubit gates also. But we are interested on only these 3 set of gates because there is a well-known theorem called universality. Like just like in classical sense, if you are given an AND gate, right? So if you are given an AND gate, you can implement any type of logical operations in that using just NAND gate alone. Similarly, using just these set of operators, you can implement any type of yeah. Along with there is another operation called Hadamard operation. Okay. So there is another operation which translates 0 to 1 by root 2 times 0 plus 1 by root 2 times 1, and 1 to 1 by root 2 times 0 minus 1 by root 2 times 1. So there is another operation, Hadamard transformation, which changes the basis, like which tilts this coin maybe from lying position to standing position. So that is called as Hadamard operation. And if I can do this rotation, control knot, and Hadamard operation, we can implement any unitary operator to arbitrary precision. So there is a well-known theorem that states the universality in quantum state. So universality. So in classical sense, if someone wants to develop a quantum computer, so the first thing that a naive person can start with is he can implement a AND gate, which is a universal gate. So using AND gate, you can construct any logical operations and you can perform any computation using just AND gate. So if someone wants to develop a quantum computer, and they can focus on this universal set of gates. And the universal set of gates in quantum, again, it's not unique, just like classical sense. Classical also, we have AND gate as a universal gate, and NAND gate as a universal gate, and similarly, we have an OR gate as a universal gate. And similarly, in quantum sense, we have multiple various other sets of universal set of gates, like various other sets, which are universal. So this is one set. So if someone wanted to develop a quantum computer from hardware perspective, they can focus on implementing this rotation and this control knot and the Hadamard operations. If they are successful on creating a circuit or creating a hardware that can perform these operations, they can perform any quantum circuit. That's an observation. Okay. And in general, if you see the quantum operations in a controlled environment, again, these major operations in a controlled environment. So here we are supposed to say that it is under a controlled environment. Okay. So under a controlled environment, now if I want to translate a quantum state to this from one state to another state, then you implement some operator U, which actually preserves this. Suppose you have alpha, beta, and you get gamma and delta. This operator U should preserve this condition. Magnitude of alpha square plus magnitude of beta square should be equal to 1. Again, this implies magnitude of gamma square plus magnitude of delta square should be equal to 1. And this condition that is, it preserves that we mathematically we call it as unit norm condition. This condition the set of operators that preserves this condition are called unitary operators. So in general, this quantum operations, the operations that are allowed for a quantum computer are all possible unitary methods. That is the whole point. Okay, so far is it clear? Like so far we have introduced how a qubit can be represented using a quantum vector, and then we try to introduce how to perform major operations on a quantum computer. So far is it clear? So do you have any questions? So I will give a break of 1 minute for questions now.
Yeah, one question from me, like how do you do the controlled environment, sir?
So
ensure
controlled
that-
yeah, so I call it as controlled environment, and that is something out of my knowledge. Like, so for example, so temperature adds more noise. So we have to so someone performing a superconducting qubit, say a type of qubit which we call it as right, someone performing a superconducting qubit. So they have to create a chamber over which the temperature is controlled. For example, and there are other type of disturbances too. So depending on the nature of the qubit, and inside this, the qubit should be protected with very low temperature, close to 0 Kelvin, like, so 0 degree. Like, it's not necessary to be 0 Kelvin, but close to 0 Kelvin.
And
Okay.
another one question, like see, if you're saying a NOT gate, then it is made up of CMOS. Similarly, if you're trying to tell this universal operators, what kind of basic device it are those, like?
Okay, so that is what I was telling about in the beginning itself. Like, so more than thinking about how to implement, so how to implement depends on the hardware technologies people work on. So if you work on superconducting qubit, you may have to think about a superconducting circuit. You pass some photons and then try to manipulate this qubit from one state to another. So that will be the idea. Like, so I'm not a very expert on that particular domain. So I'm not an expert on hardware. Okay, so I look mostly from the theory side, but the point is, if you want to develop it's kind of a switch. Like, for example, if you take a switch access information. Now, if you want to do an operations on that switch, you can turn it on and turn it off. Turning it on is a bit flip, and turning it off is another bit flip. Like, it's a bit flip operation, right? So similarly, depending on the hardware that we use for superconducting qubit, you have to apply some variation in the potentials and then change the state of the ground state of the system, and thus you change the qubit. Like, so my explanation may not be very precise, okay, on when it comes to hardware.
Okay.
So that is the thing. And when someone works on photonics based qubits or some other qubits, and the hardware technology changes accordingly.
Okay, sir.
Okay.
Thank
And that's okay. And yeah, the implementing this control not gate is it's very difficult when it comes to photons, and that is one reason people working on photonics, they don't focus on quantum computation, they focus on quantum communication, where the requirement of C naught is very less. And if you go on quantum computation, the requirement of C naught gate will be very high. And so photons are, so what I heard from my experimental colleagues is like the photons are very less prone to interactions. Like, you cannot do an controlled gate using photons. Like, that's little difficult. It's a challenging task.
Okay, sir.
And these questions you can raise it to some people working on hardware. Like, so they may be at a good position to explain that.
Okay, sir. Thank you.
Okay. And the current state of quantum computers is like we are developing qubits, and then people are implementing these gates, various gates, and they are doing some small level computations. That is what the current state.
Okay. Thank you.
Okay. And okay, so any other questions? Like, okay. If there is no question, I will move on to the next topic. Like, so now we know how to represent a quantum state. We represented it using a vector with the complex numbers as the entries and satisfying some condition, that is magnitude of alpha square plus magnitude of beta square equal to 1, depending on the position of the coin. Okay. And then second thing is we saw how to translate the qubits, like how to do operations on the qubit. So you can change, like So for example, in this case, so these two operations, this operation is called as Y flip. Okay, so I should change the color maybe to give an attention. So for example, these two operation is the bit flip operator. So a translation from green to yellow and yellow to green. And translation between these two operators is the phase flip operator, is the Z operator. And translation between these two operators is the Y operator. Okay, so that is the function of all these Pauli operators. And 2-qubit operators, unfortunately, I couldn't give a intuitive explanation based on coin toss. So based on coin toss, I can represent only 1 qubit. So when I try to represent 2 qubit using the same coin toss analogy, I have to move on to at least 15 dimensions of space, like which I cannot intuitively show you things. So whenever I have to show multiple qubits, like more than 2 qubits, I have to go for math. I cannot go for this intuition. Okay. And the next thing is, so first we saw how to represent a vector. So so represent a quantum state. So first we saw how to represent a quantum state. So that can be taking like all, it's a superposition of classical states. It's a superposition of classical states. And then we try to understand how to perform operations on in a controlled environment, or we call this as all the possible allowed operations. Okay. So once we do this operation, the next thing is, so there's a computer which performed all your operations. The operation is done. And the last thing that we have to do is we should know the result. So it has done some operations. Now we have to know the result. That is where the challenge is. Like, okay. So if you don't know the results, there is no use of all those operations. So finally, we have to read the information, and we need some meters, voltmeters or ammeters or some other measurement devices which will tell me what qubit it is like. So we have to measure it. Now the problem with measurement here is measurement destroys quantum information. So earlier we have seen when we discussed this quantum information, the classical randomness here. So suppose you do measurement, it is like you push the coin towards the same observation sphere. And similarly, when I do quantum measurement, the measurement on a qubit, so when I do measurement, it again pushes the coin along the observation sphere. For example, if I do measurement on this coin, and it pushes the coin along the direction of the observation sphere, it pushes it. Like suppose, for example, in this case, the observer was picked the point in the green side. In this particular, he may pick a yellow side too. But for example, in this case, he picked the green side. In that case, he pushes the coin along this green side. And after that, whoever sees in the same observation sphere, they will see the green coin. But they can see different versions if they change the observation sphere. Like if they change the observation sphere, like once they measure it on this observation sphere, they may get this result, like a green outcome. And after that, if they try to so after that, if I try to measure it again, and with a different observation sphere, then I will get randomness again. Okay. So is there any questions? I saw some chat box having some questions. So in chat box, someone is have some questions. Vidya Vijay has some questions with me. Hello. Am I audible? Hello.
Hello?
Am I audible?
Yeah, you are audible, sir.
There is some question, it seems like, from in chat box.
Okay, wait.
So I am getting notification.
Kindly unmute me. Wait a minute. Yeah, I'll just ask.
Okay.
Can you please type the
Okay.
question? Can you please type the question?
Okay. Maybe I will continue. You can note.
Yeah,
note
okay.
down
So
the
continue
question.
once it has been typed. I will just let you know.
Okay. Okay. So now, so suppose you measure it on this particular observation sphere and you get a result. And now, if the second person is seeing from the same observation sphere, he will see the deterministic results. So that now, which means your state has been disturbed, like your coin position of your coin, from this it is disturbed to something else. Okay, which means your quantum state is altered by doing measurement. And classical randomness also has the same property, but only difference is now you can change the observation sphere further and you can reconstruct the randomness. Like suppose you change your coin is like this and you change the observation sphere like this. Now again the coin is like with probability of it is heads green and with probability of it is which is yellow, which is not there in the classical sense, classical information. Okay, and so and the interesting fact is like so this thing, this property that is changing the measurement plane, which alters the state of the system. That is what used in one of the earliest application of quantum information, which is called as quantum key distribution. So where people share a state, like they share a coin like this or like this, with by changing it. Like so, they randomly pick one of these two coins, these two positions, these two versions of coin. Like this version. So remember, this version has two sides, either heads or tails, and this version has two sides with either heads like this or tails like this. So either standing or lying down position. And now the sender who is going to share some quantum information, they pick one of these two positions arbitrarily with the uniformly distributed with probability 1/2. They pick one of these positions and send it in the channel. And now if a third party, someone who is intermediate, like if they are trying to see this information, they can observe this particular information only if they are in the same plane. They should know the plane. Without knowing the plane, they cannot observe what information is being transferred. And later, once this qubit is passed to the third party, they can, once it is received at the third party, then they can always share this particular basis. Like they can tell that whether they have to measure it in standing position or lying down position. And depending on that, they will do the measurement. And they can they can share a particular key. Okay, so they are not going to transmit information, but instead they will share a random key which is created completely random, and that randomness is out of this quantum property. Okay, and that is one of the earliest applications of this quantum computations, quantum information. Okay, and we model this this kind of so whenever you see the coin is tilted and put it or forced it to lie it on a particular surface, we normally model it as a projection operators. Like so, mathematically, we have projection operators which actually pushes a random point at some place to the specific plane. So you call such operators as projection operators. So this measurement is normally modeled as some set of projection operators. So I don't want to go into the depth of this math, but you can think of it as a collection of projection operators, something projected to zero. So for example, if you have alpha and beta the state, and some set, and if you are measuring it in the standard plane like this, and you may get alpha, you may project it to 1, 0 or 0, 1. So you may project it. So you have two projectors, one projecting on x-axis, and other projects it on y-axis, completely two different axes. So a measurement on this plane can be modeled by two projectors. So one projector is projecting on this plane, and the other projector is projecting on this plane. And the probability of outcomes varies depending on the projectors. And the outcome is random. Remember, the outcome is random, and the outcome can be represented. So this is something called a post-measurement state. So the post-measurement state will be proportional to the projected version, and the randomness in it will be something like we model it something like this way. Okay, with this probability. So this is the probability at which we get each run, depending on the projector. So we may get multiple results with a different probability, and that is how we model measurement.
Sir, they have posted the question, sir.
Oh, okay.
Yeah, we check.
Let me see. So details of photons and polarization of a qubit. So when we do encoding on, I didn't get the full essence of this question, but what I think is like, so when we think about this photons and polarization, yeah, sometimes we can think of horizontal polarization as qubit 0 and vertical polarization as qubit 1. So you can think of, we can give a connection between photons and polarization. But so this quantum key distribution, for instance, it was not implemented through this polarization. Rather than they are implemented in the form of photon numbers. Like so, there are other properties also. Like for example, in classical sense, we can think of encoding information in different ways. For example, you may encode it in terms of voltage, or you can encode it in terms of current, or you can encode it in terms of switches. You can put a switch, you can make the switch, you can make a connection. Like for example, a CMOS, like you can take a connection. Like you can say that whether they are connected. If they are connected, then it is 1, and if they are not connected, it is 0. You can model it in that way. And all these way of modeling this information will have a different type of operation. Okay, and similarly, photons, within photons itself, we can encode this quantum information in multiple properties of photons, like in different properties of photons. And one of them can be polarization, and the other properties can be photon numbers or energy state of the photon. So these are other different properties of properties where we can encode the quantum information. Okay, and mostly from experimental perspective, I'm not sure whether people do it on polarization. Like, but what I see most of the experiments is done on this the energy state of the qubit and sorry, energy state of the photon or the photon numbers. These are the two things I have seen, but I haven't seen polarization anywhere so far. And more detailed answer, I may not be able to tell. I'm not an expert in that particular field. Like, so right. I hope I have answered the question. Like, if it is not answered, please post it. Like, post it, and we can clarify. And please be clear. Like, I am not an expert in experimental thing. Like, so I mostly work on the theoretical quantum information and quantum computation. So mostly I develop theories and I try to understand. So my work starts on understanding of qubit. I assume that we have this qubit. Like I assume that we can represent the quantum system with this particular state, and all these unitary operators are implementable. I assume that it is implementable. I'm not trying to look into how to implement this. So that may be done by a different version of expertise, which I don't have. Okay, and how to implement measurements. And we model these measurements in this manner. Like, so whatever I am explaining here is like how we model these measurements. Okay, and okay. So this is how we normally model this the measurements, like so by means of projectors. Okay, so we project it, and this mathematical object that we use is projectors, and from that we try to understand how we can do measurements, like how these outcomes are derived by the division and different set of this MIs. So suppose someone can give me this. So MIS, someone can give me this 1000 and 0001. This set of this is M1 and this is M2. And suppose you have a state psi with state alpha and beta. Suppose you have this state, and now if someone is trying to measure with this particular measurement set, and any measurement device will be represented by this set of measurement operators. Okay, so and these are different outcomes that you extract out of the measurement device, M1 and M2. And now the device will say that the outcome is M1 if with the probability psi M1 psi, which is equal to magnitude of alpha square. This is nothing but inner product. Okay, so I'm not going into the much of the details of this math. This is nothing but inner product. This psi is nothing but alpha star and beta star, where alpha star and beta star are complex conjugate. Okay, so I'm not interested in going into the detail, but I hope you should get an essence of that. So suppose you represent the measurement device by this projector set, then the outcome will be either M1 with this probability or M2 with this probability. Psi M2 psi, that is will be equal to magnitude of beta square. So this is nothing but this measurement device is nothing but that splits out, tells me whether it is 0 or 1. That is this the job of this particular measurement device. Okay. So yeah, so that is what about measurement. And then most of this explanation on coin toss and all you may not see in textbooks and or any other references that you search to understand this quantum bit. So you may have a question whether these are proper, like whether this explanation are proper. So whether I am just bluffing or whether this explanation are appropriate. So to make that connectedness, so when you do when you search for references, so you have to do the connection between whatever you have learned here and whatever you see in the references. So to see that connectedness, I will give you this particular picture. And this picture will be seen in almost every quantum, the quantum information textbooks, or every notes where we discuss the basics of quantum information. And this is something called as block sphere representation, where they take a sphere and identify the qubits from the identify the state of the qubit from the as a point in the surface of the sphere. Okay, which means suppose my coin is in this position and my point is on this point, the surface, like exactly that point is. So I pick a point, say green side. So I always use the green side as my reference side. Okay, so I can always think of always using green side as a reference side. And what I can do is, like, to represent this particular coin, I see the side of the green and I draw a straight line perpendicular to the coin. So like this, and that line intersects with the sphere at some point, and we call that point as the point corresponding to this particular position. And if you do this, map this intuition with whatever we discussed so far, it matches exactly. Okay, suppose you have state alpha 0 and beta 1, and that can this will be the normal standard representation. Suppose you represent a point like this, and it has an angle psi and theta, and this is a connection between this point and this particular state vector. Okay, and interesting is that this point is represented by alpha beta, where your alpha equal to cos theta by 2 and beta equal to e power I phi sin theta by 2. Now the biggest question is, earlier I have told the state can be like alpha beta, where alpha and beta are complex numbers. So that was that's the point that I mentioned earlier. But now I just restrict alpha to a real number. So I wanted to restrict this because my state psi and e power I theta times psi for any, so e power A, I call it as A because we are using theta in other place. So if I try to compare these two states, remember these two are two different quantum states, but with the classical observer's perspective, observer cannot see any difference between these two coins, these two things. So it is equivalent to taking a coin like this, like, and rotate it with an angle, like you rotate only the coin, you don't rotate with an angle. So you rotate the coin with the axis. So for example, in this coin, so for example, with this coin, so you rotate the coin in this direction, in this rotation, and that is equivalent to adding an phase angle of e power I A. Okay. But that has no observation, no interesting properties in terms of observer's perspective. Whatever you do, this can be taken out. So earlier we talked about a unitary operator. Even if I do use times phi, this e power I A comes out, and you will get whatever the new phi is. Okay, this e power I A will come out nicely. Whatever quantum operations that you do, it will not affect this particular phase, and we call it as global phase because it is multiplied with the global state of the system. And that is why we model whenever we try to model a quantum state, we try to keep the first element as a real number. So we can always, if it is a complex number, we can always multiply with the corresponding e power IA to cancel the complex nature of this first particular term, and we can get it real. And the second term we cannot avoid it. So we normally represent it by this particular notation when it comes to block sphere understanding. Okay, so that is another key point with respect to quantum information. And similarly, if you think about the coin on the tilted on the other side, like if the coin is flipped, then the point is flipped. Like you draw the line perpendicular to the coin along the green side. So once you draw the perpendicular side along the green side, the line will go in the reverse direction, and it will find a point in the sphere in the opposite direction. And now I will try to show some of the interesting states that we have seen. And this is our ket 0, and the point in the block sphere is this particular point. And this is our ket 1, and the point in that block sphere is this particular point. And similarly, this coin, the point in the block sphere is this point. And for this coin, the flipped version of that coin, the point in the block sphere is this point. And these are the two states. And one more interesting fact is like the opposite points in the block sphere are orthogonal to each other. For example, if you see this 0 and 1, so they are orthogonal to each other. Like, so you take 0, you represent it by 1, 0, and 1, you represent it by 0, 1. So these two, if you take, so if you know math, like, so if you take the inner product, they are orthogonal to each other. And it is not the classical sense of orthogonal, classical sense of 90 degree in this picture. In complex picture, they are orthogonal to each other. Okay. And there is another, the interesting property is we can differentiate, we can derive measurement devices. We can define perfect measurement devices that can separate out this orthogonal states perfectly. Okay. So that is another interesting perspective. So here, if you see this, like, so if you see this thing, so this picture, like, so from the first point to second point, so from here to here, so these two, if I do it on the same measurement plane, after this measurement, it is deterministic. So now this so if I don't change the plane, the observation plane, it is exactly a classical information, like a classical computation. So which means if I know this particular measurement plane, this particular coin, this position with respect to this measurement plane, sorry, this observation plane, this coin with respect to this observation plane is a deterministic coin. So there is no, it's not a random coin or a quantum coin. It's purely deterministic. So which means we can represent, we can classically, we can, even in quantumly, we can separate out these two coins separately. Like you can separate out these heads and tails separately. Whenever they are orthogonal to each other, that is, whenever they are, they have a measurement plane over which they are deterministic. Whenever they have an observation plane over which they are deterministic. Okay, and that is the thing. And the second thing, multi-qubits. To represent multi-qubits, now I may not be able to explain multi-qubits using using the same coin toss perspective. So now I have to move on to a different perspective. Yeah, do you have any questions at this point? Like,
There is a one question, sir.
oh
This
yeah,
one.
tell me. So what is the question, please, sir? Ask the question.
The person got clarified about photon, but still they have a doubt on nature of photon.
Okay. Okay, I didn't get this perspective. Like, so maybe this question can be addressed to someone who is working on photon-based qubits, like purely photonic-based qubits. I didn't get that sense of the idea on nature on photons, other than so the only nature that comes to my mind is about this polarization of photon or photon numbers or energy states of photons.
Okay, sir, you can continue.
Okay, I will try to continue further.
Okay.
So the next thing that we can look into is how multi-qubits can be represented, like how a 2 qubits can be represented using that form. So now you have 2 qubits. For example, now if you have single bit, there is 0 and 1. So if you have 2 qubits, you have 0, 0, 0, 1, 1, 0, and 1, 1. So which means you have 4 possible classical states. And quantum superposition says that your state can be superposition of these 4 states, which is like you have alpha times 0, alpha 1 times 0, 0 plus alpha 2 times 0, 1 plus alpha 3 times 1, 1 and plus alpha 4 times 1, 1. And now we need to represent 4 terms. So which means you need a vector of 4 elements. So your vector, the dimension of the vector increases exponentially. Like when it comes to 2 qubits, it is 2 power 2. And when it comes to 3 qubits, it is 0, 0, 0 to 1, 1, 1, which means 8 qubits, 8 vector of size 8. Okay, so you have a vector of size 4 now for 2 qubits. And now the thing is, to combine something in vector form, we use something called as tensor product notation. So I'm going to skip this for now. Like, so maybe someone interested in working on math, they can try to look into this vector form of the tensor products and so on. Okay, but this the two qubits which are not connected together, which we call it as entangled, which are not entangled, can be represented as tensor product of states. The state of two qubits which are not entangled can be represented as tensor product of states. That is, in some sense, it looks like this. I'm not going into deep of it. Okay, we will skip that for now. Okay, and the next important, so far, so I will move on to the next thing. And the next important thing that we are supposed to see is like, why should we do quantum? Like, what is this? Why people are mostly interested in quantum? Why we hype? What property of this quantum information helps us helps us do? So earlier we heard from we heard different things like we heard that quantum computing can perform like some very faster. It can do an exponential faster computation, and we heard many things like it can crack any cryptographic algorithm. We heard lot of statements on all those things, right? We can do all those things, and there is a limit on all those things again. So that when we enter into different topics, you will understand what is the limit on all those things too. Okay, and now all these things happen because of three main properties of quantum information. And the first one is quantum no cloning, and second is superposition and entanglement. Usually, whenever you see quantum information, people talk about superposition and entanglement. Not many will talk about no cloning. Okay, so we will. I will try to motivate these three properties, and I will give you where these three properties are advantages. Okay, so that will be the next part of my talk. Okay, and the first property is no cloning qubit, no cloning property. So what is no cloning? Now suppose I am given a qubit, and now I wanted to copy this quantum information from this qubit to the state of the system, from this qubit to some other qubit. And now this quantum properties will not allow you to copy it. So classically, you can copy a bit from one memory to another memory. You can if you have some information in your computer, you can always give a pen drive or some other hard drive, and you can copy that information to other drive, or you can use internet and send this information without altering the information in your system. But this quantum properties will not allow it. You cannot copy a quantum a purely quantum information unless you make it deterministic, unless you make it a classical information. Okay, classical information can be copied always. So this, earlier I have discussed that the quantum also can take classical states when they are orthogonal to each other. Okay, so this quantum states can take classical states, but classical states can be always copied, but quantum states cannot be copied. So that is the interesting property. And this cannot be copied because so mathematically they violate this particular property, linearity of this unitary operator. And so even quantum mechanically, this is the reason. Like so this qubit, so to perform operations on a quantum computer, it's either a unitary operator or a kind of a matrix vector multiplication, which should satisfy the linearity properties. And the other thing is it's a measurement operator, which is projection operator, which also should satisfy all these linearity properties. And now copying in the sense, what will you do when you do copying? So we bring a separate memory, which can be stored in an arbitrary state. So we bring in a separate memory 0 and bring it to the drive, and then try to perform some operation, which we call it as copying, and translate the information, that is this alpha 0 plus beta 1 to the other state, which means you wanted a system that such that you wanted a unitary operator such that you add the 0 and perform, and the resultant should be like this. It should be two copies of the same information. But the math of this will not allow that. Like you cannot get it because of the linearity property. Now linearity property says that this is violated by the linearity property. That is the only point that I wanted to highlight. Okay, so and the thing is, no cloning is the property that is used in most of this key sharing kind of information. And when it comes to, when people say that when you do quantum secret sharing and get a high level of security, there are two reasons that they claim it. So one of the reason is this no cloning. So you cannot copy a quantum information. So what people can do is you can send this encode this classical information in the quantum information, without sharing the basis over which you encode the information. The basis in the sense without sharing the information about the observation sphere. And then you pass the information to the sender, and the sender receives the whatever qubit, whatever quantum bit you send it. And now the intermediate, a third party who is trying to access this particular information, they cannot copy it. Only thing they can do is they can extract the quantum state to themselves. If they extract the quantum state to themselves, they cannot share a proper, the user A and B, the entitled users, they cannot share a proper information. So they know that they will be aware that there is a third party who has disturbed their communication. Okay, so thus it helps in security versions of quantum algorithms. But there is a problem with other algorithms that we will see later. So there's a problem. You cannot copy. That's a problem in. So we know most of your classical algorithms relies on copying. You can copy. That is why most of the classical algorithm works. But quantum sense you cannot copy. So that's a slight drawback in quantum information. But people working on quantum algorithms, they will go around it, like to make things work. Okay. And the second major property of quantum information is superposition. So, so just I have mentioned that this quantum information can take the superposition of two classical states. So remember the superposition of two classical states. Okay. So now, for example, I have talked about this state, ket 0 plus ket 1. And now, if you want to perform a quantum operation, suppose if you want to perform a quantum operation, and what you do normally, like in classical sense also, what you do, so you bring another memory and you try to compute f of x and put that f of x in this new particular memory, in the new memory. So what you do is you have the state and you bring in new memory, and then you try to do an unitary operator that performs f that evaluates f in the quantum computer, the quantum information. So the whenever it is 0, the next qubit will change it to f of 0. And whenever the information is 1, the next qubit will change to f of 1. So by this superposition, what we have attained is at the same time you can compute both f of 0 and f of 1 at the same time. And this is the advantage of quantum computation. Like this is the advantage of quantum computers. Like so, most of the quantum computers, they use this superposition property, and they develop algorithms faster. So all these algorithms from Shor's or Grover's, whatever algorithm that quantum algorithms we learn, like or we will learn along this this FDP. All these algorithms, they will use this particular superposition property. But one drawback of the superposition property is we cannot measure it. That's why people have to focus on quantum algorithms, and it is not same as classical algorithm. Quantum algorithm is different from classical algorithm because you cannot measure it. Okay,
So
but all classical, yeah, yes.
Yeah, you have a question, sir.
Yeah, please. Oh, okay, it's in chat. Oh, okay. How do tensor product of 0 has a quantum state of 1, 0, 0? Okay, so maybe I will try to explain this. Like, so the question is like, so how is this tensor product becomes 1, 0, 0? So this is the question, I think. More about the tensor products. So if you take a tensor product of two vectors AB and CD, and the resultant will be a vector of AC, AD, or in other words, okay. So in other words, it is like A times CD and B times CD. This will become AC, AD, BC, and BD. So this is how the tensor product is defined. And so mathematically, this is how tensor product is defined. So if you take the tensor product of two vectors of this form, you will get this result. Okay, have I answered the Anandraj? Like, have I answered your question? Okay, thanks. Okay. So yeah, now let us move on further. Like, and this is the advantage of this quantum algorithm, and this is and drawback of quantum algorithm is once you do measurement, now you computed f of x, f of 0, and f of 1 at the same time. But then, how will you measure it? How will you read it out? So that is where the challenge is. Like, so that's why people working on quantum algorithms, they have to work around it and try to find out f of 0 and f of 1. And the point is, you cannot do it at an instant, but you can do it nicely. Like you can do some versions of f of 0 and f of 1 that we will discuss probably in my next talk. I have planned to talk about this quantum algorithms in the next talk. Okay. And now the other property of quantum entanglement is superposition. Quantum information is this quantum entanglement. So what is quantum entanglement? Again, these two qubits, they behave together. They interact together. Like for example, consider this particular state of a 2-qubit system, which is 1 by root 2 0 0 c 1 by root 2. And this vector is allowed because magnitude of 1 by root 2 square, that is 1 by 2. So 1 by 2 plus 1 by 2 will be equal to 1. So it has the unit magnitude condition. And it's an allowed quantum state. And typically also it is an allowed quantum state. So quantum states, at least until now, it's allowed quantum state, and people have experimentally demonstrated this entanglement too. So it's an allowed quantum state. But now the problem, now the interesting fact is, now you have 2 qubits. So first is 0 and second is 0, first is 1 and second is 1. Now suppose now you create an entanglement, and suppose someone tried to measure the first qubit. So what will be the outcome? So the first qubit will be either 0 0. So you may the observer will read either 0. So whenever the observer read, they either read 0 or 1, right? And so whenever we try to read the first qubit, so what happens to the second qubit? Whenever the first qubit is 0, the only possibility for the second qubit is 0. It can never change it. And here also, whenever the first qubit is 1, if in state 1, the second qubit will be in state 1. It will never change it. So what does it mean? So if you measure the first qubit, the result of the measurement on second qubit becomes deterministic. The second qubit becomes deterministic on the same plane, right? So this is another interesting property. Like so, and again, this is also used in most of the communication related protocols. Suppose you want to share some information, what you can do is like people do create an entangled qubit and keep this first qubit with them and send the second qubit to the receiver. And then what they can do is they can put their first whatever information they have, they put it nicely on their first qubit, and later on they share this qubit based on different communication protocol. They share this second qubit to the next qubit, or they just do the measurement or whatever maybe. But depending on the measurement here, whatever outcome they get it here, the same outcome will be received at the other side. And that is the use of entanglement property. And if you see most of this communication protocols, they use this entanglement. So the idea is the cryptography, the security part comes from no cloning, and the algorithms, the speed of the quantum computers comes from superposition, and the communication part. So when you wanted to communicate, like be it quantum teleportation or quantum fast computation of classical information through quantum states, all these things happens because of this entanglement. Okay, so maybe some other talk or some other day we can talk about quantum communication in some other day. Today in this FDP I haven't planned to talk about it. If you are interested, in my webpage I have shared the slides of a talk on quantum communication. You can go through it. Okay, and that starts with, so all these slides are available, is there in that particular slide set. So the first part of that talk will be based on this quantum computation, this quantam information, and the second part will be based on a quantum communication protocol. So if you are interested, you can go through it. It is in my webpage. Okay, and that is these are the advantages and disadvantages of this quantum information. So 3 properties: no cloning, and superposition, and entanglement. Okay. Do you have any questions from now for now? So I will give a break for 5 minutes for any questions. Sorry, 1 minute for any questions.
In between, I will give a short announcement, sir, please.
Yeah, please.
All the participants are requested to enroll their attendance in the Google form. So totally, about 160 participants have been entered inside, but we have obtained only 68 attendance. So those who haven't, please So there is a question.
Yeah, how is the superposition property is used in quantum algorithms? Okay. Okay, so that is yeah. This superposition. Maybe I will take this page. So since I have space here, I will write it here. So suppose you for example, you wanted to compute, so you have a two-bit information, like, so you have, say, you have 4 students in a class, 0, 1, 1, 0, and 1, 1. And you wanted, you have some rank, like, so you have a rank. So I will try to explain the essence of something called as Brewer. So I will talk about more detail about this Brewer search in the other talk. And here I will just give you a basic idea on that so that you will see how this can be used in quantum algorithms. So now suppose the students are having a different rank. Okay, rank 0, 1, oh sorry, 1, 2, 3, and 4. So these are roll numbers and they have different ranks. Maybe you can change it to 1 and 3, 4. Now suppose you wanted to find the student with rank 1. Say you wanted to find the student with rank 1. So what will you do in classical sense? In classical sense, so now what will you do is, like, so you can go and see the roll number 0. What is his rank? His rank is 2, so he is not rank 1. So you can go to the next thing. Go and see the roll number 2. His rank is 1, so we pick it. So now at worst case complexity, you have to search for n number of audience, like n number of people. Okay, or so here you have 4, so you have to search, at worst case you have to search 4 different students rank. But then in quantum sense, what you can do is you can perform a single unitary, black, so we call it as black box. Whenever you give x, and the outcome will be x and f of x, where my f of x will be equal to 0 if the rank of the candidate x is 0, not equal to 1, and f of x is equal to 1 if rank of candidate x is 1. This is exactly this function you are searching. So this is modeling this function. Whenever you take, so classically what you do is you take the first candidate, you try to find f of 0, 0. That is, you see the rank of that candidate and you will notice that it is 2. So you will go and go for the second candidate. You go and see the second candidate 0, 1, and you will see the rank, and the rank will be 1, and you will pick that second candidate. And quantum sense, what you can do is you can model that particular f using something called a black box. This can be implemented using a quantum algorithm. This can be done. Okay, so there are circuits. That's a separate problem, in which you can develop quantum circuit to implement this part. Okay, and once you implement this, now you have this black box, and instead of sending x, what you do is you send 0, 0 plus 1, 1 plus, sorry, 0, 1 plus 1, 0 plus 1, 1. That is a superpositioned state by 2. By 2 is for unit norm condition. Sometimes people ignore that by 2 also. This is the superposition state, and they pass it through this. Okay, and the outcome here will be like, so it will be an entire version, and it will be 0, 0 times 0 plus 0, 1 times 1 plus 1, 0 times 0 plus 1, 1 times 1. So the outcome will be something like this. Okay, and now if you see, if you focus only on the second qubit, and probability of getting 1 is roughly 1/4, right? So because there are 4 possibilities, and by 3/4 chance you will get 0, by 1/4 chance you will get 1. So what we do is we do some now the idea is, like, we computed f of x at the same time, but somehow you have to extract that particular f of x, particular x, such that the value of f of x is something like this. So what we do in the Groover search is we try to amplify this particular coefficient and keep the rest of them. You try to reduce the coefficient for this from 1/2 to, so 1/2 to much lesser than 1/2, and increase the coefficient of this. What does it mean? I increase the chance of getting 1, that is chance of getting this particular state. Coefficient is directly related to probability, which means I am increasing the chance of getting this particular state that has been increased. Okay, so now after doing some number of rotations or some number of amplitude amplifications, we call the terminology that we use in quantum literature is amplitude amplification. And if you do some amount of amplitude amplification and then you do this measurement, and you at higher chance you will get this result. Remember, all these quantum algorithms are random algorithms. So we get the correct result with higher probability. So the probability of getting this value correct is will be increased. And the interesting fact is now the performance of this. Earlier you are supposed to do n searches. Now you can do it with root of n computations of this oracle. Okay. And there will be two accuracies. One accuracy is in terms of the root of n. Other accuracy will be accuracy in terms of the probability. So it may not be but the result will not be perfect, but will be accurate with higher probability. Okay. So have I answered? Like, so this is how we normally perform quantum computing. The idea is you extract f of x and do something. You have to do something, and in Brewer sense, you do amplitude amplification. You amplify the particular component which we need using this black box, and you apply that black box some root n number of times. Earlier, you are supposed in classical sense you are supposed to run it n number of times. Now you have to do it root n number of times. Okay, that is the advantage that we gain from n to root n. Now this is not exponential speed up; it is quadratic speed up. Okay, so all our classical algorithms will remain under Brewer search. All our classical algorithms will remain secure if you double the number of bits to secure them. Okay, so yeah, do you have? So have I answered your question? Okay. So now there is one more question. In real time, what would be the probability of outcome of interim zero of? Okay. So this is another interesting question. Like, so the devices that we do measure like. So you may have some measurement device. You have quantum information, say phi. You have alpha 0 plus beta 1. And these devices will not give you either 0 or 1 actually, right? So it will give you some other value in terms of, so for example, in classical, you may measure it in terms of voltage, or you may measure it in terms of current through that. You get a scalar value. You do not get an deterministic 0 or 1. Like, and now the like, so what is the probability of getting the intermediate value? And this value it depends on the state of the system. Like, so you have, suppose your state is not very much pure like this. Okay, so if it is something, so it comes from the wave function. Like, so you have so the state will be something satisfying something called as Schrodinger's wave equation, and you will have some wave function and something called as Bond rule, which says that the probability of that specific outcome will be like proportional to this particular quantity. So something this necessary, not necessary to dt, but it's integral over phi and phi star over ds, maybe like it requires both area and time. Okay, so so you may get to some intermediate outcome. This is equivalent to quantization in classical sense. In classical sense, if you have 0 or 1, you encode it in 5 volt or minus 5 volt, and then you apply the result may be like minus 4 volt or 4 volt. And whenever it is minus 4 volt, you quantize it at 0, or whenever minus 4 volt, you quantize it to 1. And the remaining part, we call it as a noise. Okay. And so here also, similarly, we have the similar phenomena. So we have an analog that has been a noise which is analogous to analog noise that has been added to your information. But then the first version of the first step to look into quantum information is to discretize them. Like, you put a threshold and make it whatever above this, you call it as 0, and whatever below this, you mark it as 1. And then there is an accuracy term that comes out here. Okay, and this will not, the measurement device in practice will not give you a deterministic result. It will be with probability, with some probability it will be 0, it will give you a correct result. Okay, have I answered the question? Okay. Okay. So, okay. So now, given that, so we have discussed this, like, so we can move on to this random qubit. Like, so far whatever we have seen. So how much time more I have? Like, how much time I have?
10 more minutes. 8
So
o'clock.
10 more minutes.
Yeah.
Okay. So if you have 10 more minutes, I will stop for 2 minutes for questions. Like, if you have any questions, we will discuss before going into the next topic. So next topic is more. So if anyone interested in quantum algorithms, they have to focus on whatever topics that we have discussed so far. That those are the basics for quantum algorithms or like other things. And the next thing is like I wanted to introduce like it's kind of a probability course in classical sense. Like so, if you are so maybe the number of people interested in that classical the probability of quantum sense will be a little less compared to people who are interested in algorithm. So I will stop here for a moment. So for 1 minute, I will keep it open for questions. So if you have any questions, let us clarify here. Okay, if you don't have any questions, I will just introduce this quantum random qubit. So far, whatever you have seen is like a classical random. You can think of as a classical randomness. Now let us think about randomness in a quantum state. Like suppose you have a system, like you have some black box which is producing your state. Like it produces psi1 with the probability 0.3 and psi2 with the probability 0.7. And in classical sense, now suppose you have an arbitrary system. Say for example, you toss a coin. That's an arbitrary system, and you get an outcome. And quantum sense, you can think of tossing a quantum coin, but then it position itself in an arbitrary position according to psi1 and psi2 with the probability 0.3 and 0.7. And classical sense, classical analogy to it is you could toss a coin, you get heads with the probability 0.3 and you get tails with the probability 0.7. And in classical sense, we model this with a vector, like or with a random variable. We map x, and x takes value 1 if it is heads, and x takes value 0 if it is tails. So you may map it to something called as random variable. And a similar analogy for quantum qubit is something called as density matrix. That's what I'm trying to introduce. Now, suppose you have a state. Suppose you have a black box that produces phi1 and phi2, two quantum states with the different probabilities, 0.3 and 0.7, which means if it produces a large number of states, if you are preparing large number of qubits, and maybe 30% of that will be in state phi1 and 70% of that will be in phi2. But we don't know the we do not know the states in between because we cannot measure it. That is the problem. And now to represent this quantum information, a good representation for that is something called as density operator. That's what we will do here. So suppose your phi1 is say your ket 0, and suppose your phi2 is ket 1. Then my ket phi1 phi0 is nothing but the state vector 1 0 times the vector. So this will be something like 1 0 times 1 0, and this will be a matrix which is 1 0 0 0. So this state can be represented by this particular matrix, and that is exactly comes here. And here similarly, if you take phi2, you have phi2 and phi2, and the resultant will be 0 0 0 1. This matrix, I say in a similar approach. And now you get a matrix which is 0.3 0 0 0.7, and this matrix has certain properties. So the example that I have shown is a classical state, but when you think of arbitrary quantum state, you will have multiple other options too. And this matrices have some special properties. One of the properties is unit trace and so, which you can go through in any textbook. Okay. And the reason why we have to see this particular representation of this particular random system is like because from an observer's perspective, whatever you do, suppose you do an unitary operator on the quantum state, and the resultant will be like if your state is phi1, so your state, so you can do this like you can do this nicely. If your state is phi1, if the system produces phi1, the resultant will be u phi1, and the density matrix version will be u phi1 phi1 u dagger, like something like this. Okay, this math part you can go through and read any textbook, but the whole point is when you apply a unitary operator on a density matrix, the density matrix translates in this form. Okay, u rho u dagger in this form. Okay, and now the fact is like now once you do this unitary operations and you do some measurement, so you do some measurement m1 and m2, so you do a measurement device which can incorporate two projectors m1 and m2, and you do this measurement. And then you will get either 1 with the probability this value and 0, 2 with the probability this value. And recall this particular probabilities is not depend on the actual state phi1 or phi2. The probabilities depends on the entire projectors. And this derivation comes from a simple conditional probability derivation. I'm not going into it, but but this probability depends purely on the state row, the density matrix row. So instead of looking into phi1 and phi2 separately, we can try to find this density matrix row and do all these operations, whatever unitary you can translate in this form, and measurement you can translate in this form, and perform whatever you wanted to do in row, and that mimics whatever you are supposed to do it on whatever you do on the system side. Okay, and that's why these density matrices are important. And this is a quantum analogous of von Neumann entropy. I will skip this part now. Like we will skip this part. Like so, this is like this is a measure of information. People who work in classical communication, they know what this mean, what entropy means. And this is a quantum version of a quantum version has multiple entropies. This is one version of quantum entropies, which is similar to classical. I will skip this for now because of time constraints. Okay, and so with this, I will stop my discussion. And before giving this conclusion, I want to have a short advertisement about this, about my institute and about doing PhD in at IITG or do research or collaborations at IITG. And the first motivation to work at IITG is it's a very beautiful place. You can see the campus, like it's one of the beautiful place here, like beautiful academic campus. Okay, and this is my department where I work. This is the EEE department. Like you can see these photos in their the respective websites. And so I work on 2 different panels. One is communication and another is signal processing and machine learning. And for now, so for us, we cannot focus on 2 panels at the same time. So I focus mostly on communication engineering thing. But I work on signal processing and machine learning too. So these are 2 interesting areas which I am involved in, like so in this particular thing. And more specifically, I work on these particular these topics. I am interested in working on. So I don't work on all these topics for now, which is almost impossible. I work on I focus mostly on error correction codes, distributed storage, and machine this reinforcement learning. So these are the 3 topics I mostly focusing on now. But I'm interested to work on, and I have sufficient background to work on all these the other topics. And the topics in the left hand side are related to quantum computing, and the topics in the right hand side are related to the classical computation and classical information. So if you are interested in doing a PhD or so, yeah, faculties, I hope most of you will have a PhD degree by now. But if you are interested to do a PhD or collaboration or internship, if you wanted your students to do a PhD with me or internship with me, or if you feel I am interesting and students can learn something interesting with me, you can drop me an email, and this is my email ID. And I will recommend you to look into this other aspects of communication and signal processing of IITG. And remember, this is the campus where the students, if they are working offline, they can work on. Okay, so with this, I will stop and just to summarize, these are the 4 questions that I tried to answer in this particular talk, and I believe I have answered most of these questions with a sufficient attention. And now I will open the floor for questions. Like if you have any questions, please feel free to ask.
And there is a basic question, sir, the qubit and bit difference.
Yeah, how do qubits differ from bits? Like so maybe yeah. So the simple point is like, so the qubit bits, you can have 0 and 1, right? The classical bit always take values from 0 and 1, which means the representation can be get 0 and get 1. These are the 2 states a classical bit can take. Okay, but quantum state can take any value. This is alpha 0 plus beta 1, where alpha and beta belongs to complex numbers, and magnitude of alpha square plus magnitude of beta square equal to 1. And the more intuitive visualization of this qubit versus bit that I have given in the in the beginning of the talk. So somewhere here, when I try to introduce this qubit, so you have a bit. So normally bit you can have this particular state, but qubit bit will classical bit will take either 0 or 1. It's kind of a deterministic outcome. But quantum bit, you cannot measure the actual state of the quantum bit unless it is a classical see all classical bits can be modeled as a quantum bit. Whatever you have classical, it has a quantum analogous. But now all quantum analogous will not have a classical analogous. So this quantum bit, whatever you have, uh, it is a superposition of two classical. It can be it's not it is always, but it can be most of the time it will be a superposition of classical states. Okay, and the problem with the quantum bit is you cannot measure it. You cannot measure the quantum state. So your measurement devices should be designed accordingly, but to measure either, for example, you can measure a classical state. Like if you want to measure 0 and 1, you can find a measurement device which measures 0 or 1, and with use 0 with the probability some p or 1 with the so in this case p will be equal to magnitude of alpha square and 1 with the probability magnitude of beta square. The outcome will vary. Like no, the outcome is not deterministic in the measurement, even if the state is a well-known state. Okay, the measurement outcome will not be deterministic, and it destroys the information. Okay. So yeah. Any other questions? So if you want to see the slides of this talk, it is there in my website too. So the talk was titled as quantum communication, in which the first half of the talk is on introducing this quantum information, like up to quantum bits. It is there in that talk. Okay. For my convenience, I will keep this page as a reference. Like if anyone wanted to see my email ID, I can have a look and you can email me. Yeah, also one more information, like if you email me, I may not reply immediately, but I will reply. Like so, it may take. It depends on my timing. Like so, at certain times I may be a little busy and I may not be able to reply it immediately. It will take some time, and whenever I at certain times I will be available. I will be available, so I can reply immediately. So it depends on the timing. So please be patient. Also, like, so don't think that I ignore your emails. Like, most of the emails I will see. I will check and reply. There is one more question. So measurement of quantum can only be probabilistic and deterministic. Am I correct in this concept? So sorry, not deterministic. Yeah. So measurement of quantum state, the outcome will be probabilistic. You won't get unless the quantum state is like, so for example, the classical state is a quantum state. Okay. So every classical state is a quantum state. So unless your classical state, say for example, your ket 0, select ket 0, you are measuring on ket 0, you are measuring ket 0, the outcome will be ket 0. It's with a probability 1, it's a deterministic. And ket 1, you measure it, you get with probability 1, the result is 1. And if you take this state, 0 plus 1 by root 2, if you prepare this state and do the measurement, then you get 0 with the probability 1 by 2 and 1 with the probability 1 by 2. So that is the, and here always I assume measurement by this measurement, 1 0 0 0 0 0 0 1. This measurement, a measurement device represented by this this operator. This is nothing but a classical measure. This is nothing but a classical measure. That is. So in the context of quantum entanglement, after superposing two qubits, if the resulting outcome has a probability ranging from 0.57 to 1, can the probability of 0.7 be considered a valid outcome probability? So in the context of quantum entanglement, after superposing two qubits, if the resulting outcome has a probability. So so I think the question is like if your entangled state is 0 0 plus 1 minus p times 1 1. This is kind of an entangled state. And if your P is greater than 0.57, can we think of P as 0.57? Can we assume P as 0.5? So, so Anandraj, am I clear? Like, so can you open mic for Anandraj, or like, I didn't get the question properly. Like, hello.
Sir?
Yeah. So it's a question. So I'm trying to understand this question. Like, question by Anandraj, Mr. Anandraj REC. So yeah.
Suraj,
So
sir, can you come up with your question?
okay, he's not able to unmute it.
Unmute, yeah.
So am I right? Like, so in this understanding, am I right? Like, so you are trying to state your quantum state as like this, like p times 0 plus 1 minus p times 1 1, and your p is greater than 0.57. And so your question is like whether you can assume that p is 0.57. And can we consider that? So the thing is, so if you can consider it, but then the result. So this probabilities, all these probabilities, actually we use these probabilities for our understanding. Like, so the quantum. So again, this is not p. This is root of p and root of 1 minus p. Okay. So now when you do your understanding with respect to 0.57 and you do perform the quantum state is with a different value of p, and if you perform all your analysis with assuming that it is 0.57, then the result may mismatch. So a simple trivial example is if your p is 1, then the result is 0 0. You will always get 0 0. You won't get a 0 1 1, right? If your p equal to 1, it's a deterministic state. And now if you try to say that you are trying to construct a random result with a probability 0.57, and you construct a quantum state like p equal to 1, and then you do repeated measurement, then you will fail. Like, you will get 0 0. You will not get the actual result that you are supposed to have. Okay. So it depends on the context. To be specific, it depends on the context. But in most of the context, it will give you a wrong direction. Okay. And yeah. Okay. So there is one more question. Quantum computing is under research, or else it is implemented in real-time application. Also give the details. So the point is, so now at this point there are various companies, various startups, they have started implementing quantum computer, and the only thing is they are not up to the mark of applications. Like, we don't have a proper quantum computer which gives you a very good applications. Like, so you applications that beat classical computers. So this quantum Google, they claim that Google, and I think IBM also they claim, but they claim that, so all these are in paper. They don't show it in public. Like, so that we have that result, like that we can perform some classical algorithm in using quantum computer, which is faster than the classical algorithm. But then we don't have a prototype of a real application. Like, so that's a mathematical model. Like, so they have solved a problem which for now we don't have a proper application. Like, it's not into the application. But one side, like, so this quantum key distribution has come to the applications a long back. Okay, people like, so when I was doing PhD itself at IIT Madras itself, there are faculties who are working on who worked on this quantum key distribution, and they have succeeded on transmitting this, sharing this key between two remote people located at say 100. At that point, it is people have succeeded with 100 meters and so on. Now I heard that people from China and all, they have succeeded some 1,000 kilometers and so on. So, but all these are like, so I am not in a position to verify the results, but these are some news that come up. Like, okay. And our quantum mission also has this goal on developing a long range quantum communications. So that's a one part of goal. yeah, so where can we apply quantum computing in electrical engineering? So one, okay. So one application of quantum computers is like, so we use quantum computers to speed up things. Like, so one, so for example, so I discussed three properties for no cloning and superposition and entanglement. So the thing is, we have to come up with applications. So some of the applications that are already there is like mostly on communication. Like, so people who do communication, they can if they have a quantum version of communication, they can do something. Uh, they can share a key securely. That is what it's proven now. That's what experimentally proven now. Okay, and then from algorithm side, we can solve problems whatever is impossible using a classical computer. Suppose, for example, searching a student's roll number. Suppose you have a data of say 1 lakh or 10 power 1000 students. Sorry, 10 power 1000 is 2. Let us keep it as say 1 lakh or 2 lakh students. Now you wanted to search a student with a certain mark, like or certain rank or certain mark rate. You want to find out one student, and then now suppose you try to use uh, classical algorithm. You have to search through all this 10,000 students one by one. But then when you use quantum computers, when it becomes practical, if you do quantum computer, then you can search it in very faster time, like square root of 10 lakh, 1 lakh time. Okay, so you can speed up the computations, all these machine learning, all these other algorithms. So everywhere they speed up the existing algorithms. That is what we do. So quantum computing by itself, it helps in electrical engineering by solving the problems involved in electrical engineering, not like so I don't have the other way to say. Like, so the only way that I can say is like, so there will be some mathematical the analytic problems that cannot be solved, like that takes longer time to solve in electrical engineering, which can be solved faster using a quantum computer. So that will be that is where the quantum computing will help in electrical engineering, and the electrical engineers can help quantum computers. That is another perspective. Like, so people working on especially VLSI domain and photonics domain, and those people they are working on developing this quantum computers. They can help quantum computers, that quantum computing to come up to make it more practical. Like, so yeah, that will be the another thing, like another perspective of quantum computing in electrical engineering. Have I answered? Like, Vice Principal JT. Can you use quantum technology in a classical computer? So yeah, so the point is we can simulate a quantum computer using a classical computer, but we cannot uh, so implement a quantum computer in a we cannot use quantum technology in a classical computer. And maybe some of the recent some of the first quantum application or the first level of quantum computers will be like a mix up of quantum and classical computers. There is a class of algorithms in this quantum, like people call it as so variational quantum algorithms and so on. Like, so that is like a mix up of a classical algorithms and a quantum algorithms. And using quantum algorithms, they simplify the problem and they do it on classical. The simplified version will be implemented on classical computers. And now the quantum technology works on completely different hardware. So now to use quantum technology in a classical computer, we wanted the hardware to be changed. So we need hardware that supports quantum qubits, like for example, qubits. So the hardware should support qubits. Now, whether the qubits can be incorporated into this particular the system that we have, that is a that's a big question that may be answered in the future. Like in future, maybe after 10 years or so, we may have a quantum computer in our hand. But now in the near future, we don't see a quantum computer in hand. Like so we cannot have it. So whatever we can do is we can simulate all the algorithms that we develop in a classical computer, but we cannot really implement it. That's the point. Yes, Kavita, have an answer?
So can we wind it up?
Yeah, if there are no questions, we can wind it up.
Yeah, it's because the other speaker is waiting, sir. He's
Yeah,
having.
yeah, sure. Yeah, please. Yeah, wind it up. So if you have any questions, you can email me. Like we can.
Yeah,
have a
yeah.
separate one.
Request the participants, like if you have any questions, please email to Arun sir. That email ID is being posted in that PPT, please. So it was a wonderful
Okay,
session, Arun sir.
Yeah, thanks.
Yeah, and on behalf of all the participants, I would like to extend our heartfelt thanks for the insightful session on Introduction to Quantum Computing. The way you handled starting from the quantum gates, took over the quantum measurement, and you given an introduction about the Grover search and all the three principles of no cloning, superposition, and entanglement. Everything was very pretty clear. And it was like you have initiated a great interest on this quantum computing. So thanks for your expertise and effective teaching style, sir. It was very clear and informative session. So once again, I thank you for your time and dedication on behalf of all the participants. Thank you so much, sir. And I'll request all the participants, if they have any question, to post you on mail.
Yeah, and if you are interested to work with me on any sense, like you can email.
Yeah, that's a great
And
news for the participants.
I also request to encourage all of your students to look into this IIT Guwahati and EEE department at IIT Guwahati, and more specifically my specializations, communications and signal processing. And if you are interested in either working with me or other colleagues here, like it will be very good. Like,
thank you
if you are
so
interested, you can feel free to contact me.
Yeah, thank you so much for your session, sir. And I request the
Yeah.
participants, if you wish to have any questions on this introductory session, please feel free to mail your questions on the mail ID that has been provided on that PPT. Thank you so much, sir.
Yeah, thank you. Thank you for the opportunity. Yeah,
Thank you. Thank you. So
yeah, we will meet again in the
we
other
will
session.
meet again in the next session. Yeah, thank you. Thank you so much. I may request now our proud alumni, Setu Parimi sir, to continue the session on cryptography and cloud computing on using quantum. Yeah. Please, sir.
Yeah, sure. Perfect. So I'm audible, right?
Yeah, you're audible.
I'll just quickly share my screen. Okay. Let me know if you're able to see my screen, by the way. Are you able to see my screen?
Yes, sir. We are able to see you.
Perfect, guys. So, good evening, everyone, and just introducing me for the second time. So, myself, I'm Setu Parimi, and I'm an alumni at Rmkcet group of institutions. It's since my college days, I got into my cybersecurity domain and been doing it for almost a decade now. Majorly into application security, cloud security, those type of things. And has been a practitioner and research publisher at some international world's biggest hacking conferences like Black Hat, DEF CON, those type of conferences in past. Because I did my master's in US and then I was working in US for 4 years before moving to UK. Once I got bored of my full-time job of 9 to 5, I decided to take an entrepreneur hat because in my previous organization, while I was working for Amazon Web Services, there were a lot of problems that I have seen that big enterprise organizations were facing in different aspects. So I thought like, okay, why can't I go ahead and solve those problems? And then I did quit my job and started building Risk Profiler, which is my startup, and it's VC backed. We have top chief information security officers in the Bay Area, East Coast, from the New York as our angel investors. And we started with 4 employees, and now we are like 25 employees. All the development and research is completely, and operations is completely based out of India. And proud to say that we have 4 alumni of, again, RMP group of institutions as some senior developers and senior engineers at Risk Profiler. So I would like to thank the management for giving this opportunity, and looking forward for a fruitful session. If there are any questions or anything like that, I'll be happy to take them at the end. So we have like an hour, and the first 45 minutes we can go through various things, and you can keep shooting out the questions that you have over the chat. And once we wrap up the deck, we have 5-10 minutes for the Q&A kind of a session. If that is not enough, I'll be happy to share my contact details, and always happy to answer or have a coffee chat to discuss in-depth set of things. So I think for the past few couple of hours almost, we have been we have been taught on quantum computing by Arun in an amazing way, covering all the basic stuff. So there's a huge difference between the way how Arun would explain and me would explain, because Arun is a seasoned professional teaching kind of a person, and I'm more of a practitioner kind of guy. So I may be very bad at explaining things, but happy to show them the hands-on kind of stuff as well. So yeah, to start with a quick high-level introduction, what is quantum computing? So it's basically a computing mechanism that leverages the quantum mechanics to process the information. And we did have a very detailed explanation around what's the difference between a classical bit and a quantum bit. So as Arun has mentioned, right, if you take a simple coin and then flip it, you get either heads or tails, unless or until it stands in a weird stands out in between, in some cases during the cricket matches. Apart from that, majorly it's always 0 and 1, right? So in a classical bit, that's what it is. But when it comes to quantum bits, you have a ton of information in that quantum bit. You can tell that, the quantum bit will tell you that, okay, there is 40% that it can be 0, 60% it can be 1, and it can give you a lot of variations, superpositions, and all that stuff. So that's what the major quick difference between a quantum bit and a classical bit. You may always ask me a question like, okay, can you please simplify it? So to simplify it, right, if a normal computer is saying yes, and if the normal computer is saying is no, the quantum computer would say like, yeah, yes, and no. So that's the quick difference. It can have the information of both the bits, 0 and 1, and also some information in between as well. So again, explaining a bit more in depth, right? So Arun did show you the information around how this simple coin keeps on flipping, and if it is towards this, the more percentage is towards head, and if it's towards this, more percentage is towards tails, and that's the probability. But if you change the sphere, and then the probability changes a lot. So basically what it is, it like the entanglement, it allows you to go ahead and store a lot of information, and that being interdependent enable powerful combinations. So that's the quick thing about qubits. And we always can compare like, okay, how can a classical computing differ from quantum computing? There are some minor things. So the first thing is the foundation. It's the binary zeros and ones in the classical computing, whereas it's 0, 1, and both or between it, and you can have a ton of information. And that's what makes it amazingly super speed for quantum computing to provide all these reasonings and take the patterns around whatever the approach it can take, possibilities, and then reach the right solution with a lot of permutations and combinations with the patterns. Whereas in quantum computing, you have to go step by step kind of an approach. And when you talk about the speed at which this both goes, it's always, classical computing is always amazing and quick for linear problems. So if you go ahead and tell like, okay, what I need is just 5 into 3 is what? The classical computing will quickly tell you 15. And the quantum computing will tell you that, okay, it's 15 and the probability percentage is 80 or whatever it is. It gives you a lot of additional information, and it's not wise to use quantum computing for basic things. Like you can go ahead and quickly slap a mosquito and it dies. But if you take a huge hammer and try to hit it, and that's what you're killing a small problem with a huge compute power, and it's not optimal for the resources as well. In terms of errors, majorly, so when it comes to classical computing, right, we have very few errors because it does not think about a lot of possibilities, reasonings, all the patterns. It doesn't take it. It's like it's straightforward approach. It takes it, and then it just gives you the output. And the number of errors that you have with the classical computing is way low compared to quantum computing, where there's a lot of probabilities and permutations and patterns it takes to come to a solution. And even that solution would be 70% right or 80% right. It's a bit same in the artificial intelligence side of things as well. For example, if you use a image comparison machine learning model, what happens is you use AWS services to go ahead and run that machine learning model, and you can use SageMaker and those type of things. And once you go ahead and run a model asking you like, okay, is this image what belongs to the president of USA, Donald Trump? The model will definitely tell you that, okay, it's 90%, it's 95%. So it always gives you that percentage kind of a reasoning. That's what happens with the quantum computing as well when it comes to error handling and those type of things. And you may have heard a question like, is quantum computing already in place, or is it not yet ready, or it's being built? So those type of things. So there are two answers for it. So there's an official answer and there is an unofficial, strongly believed speculation as well. So quantum computing, they came out in the early 1980s, 1950s. But there are some advanced algorithms that were written in 1990s that showed a lot of advantages of quantum computing, especially in cryptography and those type of things. And in 2010 and 2020, we have seen a lot of public service cloud providers like AWS, Azure, Google Cloud. All these public service cloud providers have been offering quantum platforms at a commercial development level. So what is the meaning of this is, for example, if you just quickly go to, okay, let me get rid of this. Okay. Anyways, so if you just go to AWS quantum computing, they have a service, and the name of the service is Amazon Bracket. So the same way you have a similar services in Google Cloud and also in Azure. So the beauty of these things is like, and you don't need a huge physical compute to go ahead and run these things. It makes your life a bit easy when you want to go ahead and quickly try out quantum computing by yourself. There are these are very amazing services for you. And I know this for a fact. Like I have been working at AWS in my previous role, and they do have a ton of research credits that are available for educational and research institutions that are out there. So you can always go ahead and submit out. I don't know where exactly you need to search for, but it should be like something like AWS-research at Amazon.com. So it should be something like that, where AWS, those type of organizations supports you to do a lot of research kind of things. So I would, if you're not having this, I would strongly recommend you to go ahead and apply for research credits and get those research credits, and you can try on all these things. So, for example, this is how it looks like. So these are some physical bare metal servers that are out there, and you can I mean, AWS do have, I mean, just like AWS, any other public service provider also have this. So they have like 34 qubit bracket vector simulators, and there are 50 qubit and there are 17 qubit. So these are some hardware providers are from the Amazon Web Services. At the same time, any cloud provider will always love partners because they know that they cannot be expert in one particular area. So they want to partner with some small startups or small organizations that are very proficient in those niche areas. So, I mean, IonQ and QERA and Rigetti, these are some partners of AWS, and they provide this type of computational instances for you to go ahead and run your notebooks. And you can always go ahead and create your own notebooks. So you can create these notebooks and run it. I mean, once you create this notebook, right, you can give an information, for example, right, it's RMK research. And you can just set up some basics of, I don't want to get a huge bill. So you can always configure the inactivity, but yeah, here it is. So you can choose whatever the instance type, how big you want to have the GPU for your notebook instance. And once you configure all these things, you can also configure what public repo that you want to have access in this one. So for example, right, even when we talk about popular quantum computing algorithms, you always have the flexibility. Just Google for AWS Labs, and then you get quantum computing. Yeah. No, AWS Lab bracket. Just search for AWS Labs bracket, and then add GitHub at the end, and you get the bracket labs over here. So these are the bracket labs that you can use to go ahead and run these notebooks. These are majorly some research and POC codes, those type of things that you can use. On the other side, you also have some popular algorithm library. Yeah. So there are a lot of popular algorithms that are out there. And these are like, for example, we will be talking about Grover's search. That's a popular algorithm. And the shorts, this is another popular algorithm. So these are, I mean, the reason why we will be talking about these type of algorithms today is basically because these algorithms do have the potential to break the encryption that is out that we are using right now. So that's the reason we'll be discussing in a very, very high level in terms of these things. And if you ask me questions around like, okay, what's the underlying logic for Grover's algorithm, or if you ask me what is the underlying logic for Schroer's algorithm, I don't know anything about it. The reason why I don't know anything about it is it's advanced math, and after a given point of time, it just goes Hail Mary kind of a thing. So the guys who are like damn experts in mathematics or applied mathematics, so those are the right folks for those type of things. But I know what algorithms to use and what enterprise organizations use, what are the use cases of quantum computing. So those are the things that I'm aware of, and happy to have those type of discussions. But if you want me to go underlying the hood and talk me about those things, I would leave those things to the amazing PhDs that are out there. So I think I just see a hand raise happening over. Okay, I don't know, maybe I just saw it wrongly. Okay, perfect. I'll just continue. Yeah, I mean, these are, I mean, let me create these notebooks as well. So for example, you can always have, yeah, this is an algorithm library as well. So the Grover's algorithm that I was talking about and Shore's algorithm that I was talking about, the code is already available for you because this was written by employees of Amazon or some open source AWS community heroes, those type of folks. And you can always use this code base to go ahead and create notebooks. And from the notebooks that you have created, you can run the quantum computing algorithms. So, I mean, we can discuss these things down the road. So let me come back. So, I mean, the quantum computing, the reason why I did show this all things is it is there in production. So there are some big enterprise organizations, financial services organizations, and stock market prediction organizations, and even government organizations. Like, for example, there are like intelligence organizations, cross borders with internal intelligence. All these type of several organizations, including the state hackers, state acting hackers, they use quantum computing for various different use cases. As of today, that's officially known, and unofficially you don't know because it's always 5 or 10 years later. It's always 5 years later where the normal people like us, we get the information that government or some state post that some kind of technology has been out there, and government or military has been using it for a lot of different type of things. So the solution to it is like quantum computing is there and it's not going to go anywhere. It's going to be there for the future as well. And it's time for security professionals like us, like me and other folks to learn security side of things in the quantum computing world and help the wider audience to improve their security posture that are basically affected due to the quantum computing attacks. So we'll be talking about these things here. And if you ask me, like, okay, Setu, you have been talking about quantum computing and you have been talking about cybersecurity. How the heck these both are? How are these both linked together? So the reason how these two things are linked together is by various cybersecurity needs. And one thing that we'll be diving deep a bit is cryptographic protocols. As we may all know, there are some pretty good standards that are out there that are published by top non-profit research organizations and being used by global enterprise organizations, global audience to secure their communications while they're communicating in the internet. For example, right, I mean, I have been talking to you folks and you're listening to me. How can you make sure that there is no server in between across the world where the bits and bytes have been transmitting to reach your endpoint devices? It's not being tampered or it is not being sniffed. So the way how it is not being sniffed, because internet is not just a single server. You got communications, like it's a backbone. It's dependent on a lot of ISPs that are out there, internet service providers that are out there. So any communication that happens between me and you will be traveling through at least 5-10 different hops or endpoints. And all these endpoints do have the capability to sniff the traffic, whatever is transmitting through their network. So all these are like edge routers, or there are some border gateway protocols that can be used. But it all depends on how encrypted are you communicating with your end users. It becomes that hard for those man in the middle kind of attacks to happen. To talk about the NIST, right? So what are the standards? So who sets the standards and what are the standards? So there are some non-profit organizations, like for example, NIST. So NIST is basically it's the US government. What they have is it's National Institute of Standards and Technology. These guys are pretty solid when it comes to cybersecurity standards, and they do have pretty encryption. So they do have pretty solid encryption standards that are out there that they issue to their, to not just to their own government entities, but also to the wider world that they can use and implement in their organizations for a better cybersecurity posture. So I think I'll be coming to this very interesting topic later in the talk. But the high-level cryptography, like for example, right, what are the block ciphers techniques? What are the digital signatures that are good to use? On all those things, NIST dictates it, and they don't dictate it, they suggest it or they recommend it, and those recommendations are highly valued, and they are always highly respected, and they will be implemented by a lot of solution providers for their customers for the ease of use. Coming back, right, these are like different type of standards. For example, if it is public key based, there's a FIPS standard. So you may ask, what is FIPS? So FIPS is heavily used. It's in, for example, right, there are private keys and there are public keys, and we all are using browsers, right? So we are all using browsers, and in my browser, what happens is we use certificates. So all these certificates, for example, this is a let's encrypt kind of a certificate. So looks like the NIST, they have their own public key infrastructure. They create their own certificates. They don't rely on anyone else. They create their own certificates and they have their own management sort of things. And if you look at, this is GitHub, and the GitHub uses Microsoft, I believe. So let me check the certificate. So GitHub uses Sectigo. So what is the meaning of this is, you are in a public world and you're trying to communicate between each other sitting far away, and the way the communication happens is there is a public key, there's a private key, and the public keys and private keys are all encrypted with a different key material. So that is with these guys. So you can always question like, okay, I have the public key and my information is being encrypted using I have a private key and my information is being encrypted using a public key. How can I be sure that the provider called as Sectigo ECC domain validation is not using the private key that they have to sniff all my traffic? So it can be a huge problem as well. So I mean, the way how it works is these certificate authorities, they are certificate authorities and they have to follow some standards called as FIPS standards. Only then Google Chrome will add that certificate authority to the browser's whitelisted root certificate authorities. So the meaning of FIPS is if anyone, even the employees of Sectigo, if it is a FIPS standard, and if the employees of Sectigo wants to FIPS server, yeah. So this is how it looks like under the hood, the console servers. Okay, so all these private keys and all that stuff, they are all stored in these servers. And the way how these are very special is you try to remove the hard disk, right? The entire data gets deleted with advanced deleting algorithms. So those are the FIPS standards. So the standards are set by NIST, which is a non-profit body, governmental body, and those have to be followed by these guys.
Sorry for interruption. There is a comment stating like your voice is not audible enough.
Oh,
Like, yeah.
is it only for? Are you able to hear me, by the way?
Yeah. I am able to hear you. I don't know, but I think like you can be a little bit louder.
Okay, Professor.
This moment only I got the comment. Yeah, please continue.
Thanks for calling me Professor, by the way, Nidya. I'm not a professor, but it's always good to be called as Professor. So thank you so much.
Yeah.
Anyways, I think you just have to fix your internet connection. And I always do have a habit of talking a bit fast. I try to slow my pace as well. So yeah, I mean, what we were talking, yeah, FIPS. So these are some kind of standards that the NIST body tells or suggests. And there are so many organizations, even for example, your credit card information. So the credit card information is stored somewhere in plain text. How can you make sure that organization employees are not stealing the data? So you may use Razorpay. Razorpay is pretty popular in India, and Stripe is very popular across the globe. So these are some payment gateway providers. And the way how Stripe, Razorpay, these type of organizations do have all this stuff is they do encrypt all this data and then they store them in a FIPS certified device. What is the meaning of that is if anyone tries to tamper it, the data is gone. So that's what it suggests. So, and even the symmetric encryption, there are advanced encryption standard AES and SHA, HMAC, SHA3. So there are some advanced encryption standards, and even these standards are defined as well. For tools, there are some guidelines how to use the hash. For the key generation, what are the guidelines? For the key management, what are the guidelines? So there are some multiple standards that are out there, which are very, very powerful and which are very respected as well. So those things are being used. And out of this, right, if we talk about, okay, what are the encryption cryptography protocols that are being widely used out there? So there are two types of encryption, right? We all know. One is like symmetric and asymmetric. If you ask the advanced cryptography guys, they will name 2 or 3 more like polymorphic encryption. They have like 4 or 5 more, but let's stick to the basics. In the basics, there are symmetric and asymmetric. And in the symmetric, the concept is very simple. We all know that it's you use a single encryption key. Symmetric. In asymmetric, you have one encryption key to encrypt, and the other one is to decrypt. So there are some popular algorithms that are out there: ECC, RSA, AES, SHA2, SHA3. These are some popular algorithms that are out there, and there are some multiple variants. I mean, you can call them as versions. So multiple variants of each and every algorithm that is out there, and each and every variant has its own key length. 99% of the time, that variant will have the key length as their suffix. That's what it will be. So now there are so many amazing security standards. Now there are so many amazing, what is this called as security protocols with a way higher key lengths. So we can always think that, okay, now with all these amazing Avengers kind of security protocols, we have our communications secure, both in transit and at rest. So you may also ask like, okay, Setu, how are all these, how much widely are these encryption protocols used? You may ask this question. So the RSA is the algorithm that is used for all these SSL certificates, TLS certificates, all the certificates that we have on your websites on between the communication happening between Zoom endpoints as well. So most of the time it's RSA. And there are also some IoT devices that are out there. So the IoT devices have smaller chips. They have small computational powers on the IoT devices. So what they do is like they don't want to use some encryption algorithm which is a bit computational heavy. So they want to use some kind of algorithm like ECC kind of algorithm, and that gives them equivalent to RSA 3003K kind of an security at just 256 bits. So there are some ECC. This is also a very popular one used in a lot of IoT endpoints. And the third one is AES encryption. So you can always go ahead and, you may always use these kind of softwares, right? Folder locks and some kind of file vault kind of things, right? Most of the time they use AES encryption, and that's pretty standard out there. So the use cases of these major encryptions algorithms are these things. And if you want me to show you, right, like, okay, can you show me what these things are out there? You can, this is same with any cloud provider. For me, it's a bit easy to use AWS. So I'm just showing it on AWS. But if you go to Azure or if you go to Google Cloud, it's pretty much same. So the key types are symmetric and asymmetric. And the key usage can be encrypt and decrypt. And the other one is generate and verify MAC. And this is kind of thing that you use to configure single sign-on, SAML applications, those type of enterprise applications where you want to authenticate and have the message digest and those type of things. You use this HMACs. But even if you consider encrypt and decrypt or anything like that, the key spec is always there. The HMAC is one type of algorithm. And if you go to advanced kind of a thing and external keys to DNS. Okay, here it is. Now you get it. So you get like RSA. So these are the key specs. So you may think like, okay, Setu, why these guys are even providing these two options when RSA 4096 is the most advanced one? Yeah, earlier they were supporting the lower versions of RSA. They were slowly migrating to the advanced versions, and they are slowly retiring the older versions. At the same time, you also have to consider in production workloads, you have to consider if you have huge advanced applications or compute intensive applications or input output advanced applications, which requires a lot of input and output read writes at scale. What people do is, for example, I don't know how many of you guys do play PlayStation. So in PlayStation, there are amazing games that are out there, and some like Call of Duty and all these things are amazing games. So those games have very high advanced computation needs, and those things have to connect to a remote server, and then those servers will be connecting to other players. All these like hundreds and thousands of players will be playing simultaneously, and you don't want to use an algorithm that makes your application slow by 2% or 3%. So I did work at an gaming organization in past. It's a pure product-based company. It's a solid security engineering team over there. They did agree to not use any kind of encryption just to make sure their application or their game loads 40% speeder. So if you disable encryption, your gaming experience is 40% faster. So it depends on what type of the more the number of keys, the more time it takes for the endpoints to encrypt the data and transmit it. It is secure, but it takes a bit more time. So you have to consider all these things when you're architecting the applications. But this is the key spec. So RSA, the reason why I'm showing this is the RSA is pretty widely used. And if you look at this ECC, so this is NIST, the NIST standards P56, P384, P521, and 256K1. So these are some ECC algorithms that are out there as well. So any provider, how can you believe that, okay, I'm going ahead and buying a certificate or I'm buying a key, encryption key. How do you believe that, okay, it is secure? The way how you believe it is secure is these are the algorithms that are telling you that they are secure. Pretty solid ones. So yeah, let me come back to the deck. So these are some algorithms that are widely used, and these are the algorithms that are used on a daily basis to secure your digital experience across the globe. And you may have a simple question like, okay, how do you think AES and what is the underlying hood or underlying magic of AES encryption? So I did study this in my third year of studying at our RMK group of engineers. There's a network and network security kind of an subject, and I was studying this. And then for cracking interviews, I studied some time at Amazon or those. They dive deep on all this. What is the concept of AES? So I studied, and now I forgot what it is, half of the stuff. But in a very nutshell, right? So AES again is a symmetric encryption algorithm. So there is no public key, no private key. There's only one key that has to be pretty strong, and the key size can be 128-bit, 256-bit, or 512-bit. So the advantage of it is, so if you have a huge key number, right, it's always very hard to guess that key. So for example, if you have a password 1234, how easy is it to guess versus some random numbers like 1914, whatever it is. So it makes it hard. Now this is just 4 numbers. Make it 6, it becomes a bit more tough. Make it 12, make it 100, make it 256, make it 512. That's how the key strength is. The higher, the longer it is, it takes more guesses, more brute forces to go ahead and identify the actual value of the key to crack that algorithm. So it's also designed in such a way, that AES algorithm, it's also designed in such a way that you're giving, I mean, always guys, security is not just an amazing issue. Security should be at the cost of business, or at the cost of not killing the experience of the end users. So for example, people don't like security that stops them at doing something. So security should be there, but it should not kill the user experience. The same way AES algorithm has been designed to be computationally efficient for modern processes, so that it can give a lot of advanced protection. At the same time, it can be done with minimal computation power as well. So that's a very quick high level overview of AES. And there is also RSA algorithm, which is being used, as I mentioned, for the certificates and all that stuff. So for even when you talk about certificates, right, you can always go to, again, any cloud provider and certificate authority. So this is a certificate authority, is again a different service. You can always create the certificate authorities. Actually, let me create the certificate. No need to create the certificate authority for just to create a certificate. So let me just directly create a certificate itself and show you how. Okay, request a certificate, request a public certificate. Yes. And now, if you look at this, right, RSA algorithm. So RSA algorithm is also used in your web traffic. So for example, if you have an application in your organization, and that's rmkcet.ac.in. So even rmkcet.ac.in. Okay. Even this organization, I mean, this individual domain, it has its own certificate, and it's issued by some certificate authority, and this certificate authority is using some kind of encryption algorithm to go ahead and protect the endpoints. So those things will be over here. So just have to, if you just scroll this, right, you get what is the encryption algorithm that is used. This is SHA-25. Okay, here it is. These are the values. So these type of 256 values and those type of things makes it always difficult for cracking the algorithms, and it's also pretty mature. And the same thing with ECC algorithm as well. A lot of, I mean, there's one fancy stuff over here. It's a elliptic curve discrete logarithm. So if you ask me what it is, it's a bit hard to tell me like what exactly it is. But the mathematicians know it. But under the whole, in a nutshell, right, it finds a key material that can be used to encrypt the data, and that key material is calculated using the prime numbers and factors. So it's always two big prime numbers multiplied to form a big number. Now, if you have those two prime numbers, if you're able to factor that huge number back to those prime numbers, you get that ability to get the private key. So in the same way, ECC also has comparable security. Like for example, a simple 256-bit ECC key provides 3072-bit RSA key level of security. So it's pretty compute efficient. At the same time, it gives you the amazing security sort of things. And these are some encryption protocols that are out there protecting us on a daily basis. So now we can always assume that, yes, we do have very strong encryption methods that are out there securing our traffic. And we always have to think again. So just like how Thanos can go ahead and do amazing things at a single snap, there are amazing computational powers that can do or that can kill RSA, that can kill AES, that can kill ECC, or that can kill SHA-2 with just a single snap. And that's the Thanos introducing as quantum algorithms. So you can always tell like, okay, how can a quantum computing algorithm can crack the highly reputed encryption standards that are out there or protocols that are out there. So it has been proven that few algorithms, the quantum computing algorithms, have been used to crack these things. So for example, right, there is an algorithm called a Shor's algorithm, and this is the algorithm that I was showing you guys. So if you just let me close this. If you just go back to Bracket, which is the service from AWS, and if you go to algorithm library, and then Grover's is over here, but sure, yeah. So yeah, so this is algorithm, and this algorithm can be used to go ahead and identify one thing, which is basically the prime numbers. So you have to solve that mathematical problem of finding the prime numbers and factoring them. And if you do that, that's, I mean, the way how all these encryption algorithms are created in the first place is assuming that, okay, reverse engineering this huge key is a huge, it takes millions of years, it takes hundreds of years. So assuming with all these kind of things, the initial algorithms have been created, but over a period of time, the different technologies came out, including the quantum computing, and it made very easy for cracking or solving these problems. And there is also another algorithm called as Grover's algorithm. So what does Shor algorithm, I mean, what does Shor do is it goes ahead and does integer factorization. So what is the meaning of that is it can, if you give it a huge number, and if you ask me like what are the primes that are used to create that integer, it can give you that those two primes way faster. And the Grover's algorithm is heavily used. For example, we do a lot of hacking kind of things, ethical hacking kind of things in the dark web, and we collect a lot of hashed passwords. So what is the meaning of a hashed password is if you're using an online web application, and that application can be RMD or RMK, whatever it is. So if you have an application over here, and if there is a login URL or anything like that, I don't see anything over here, but if you have a login URL over here and it has a username and password, in the back end, right, the username and password is not stored in plain text. If they store in plain, I mean, people do sometimes store it in plain text. That makes their life easy, and that makes hackers' life also easy. So sometimes some good folks, they do encrypt, they do hash those passwords, and they store them. And once they hash them and store them, it becomes, when hackers hack to that kind of a database, it won't be plain text password, it will be all hashes. Can be NTML hashes. There are different type of hashes, NTML hashes, SHA, I mean, MD5 hashes, those type of things. But the beauty of the Grover's algorithm is it will guess, okay, for example, if you tell like say2 is the plain text password, and it has a huge hash. So this hash, it has to be reverse engineered in such a way to check with the huge dictionary of a million breached passwords. It will check one by one. Okay, is this password? Is this the password? Is this the password? And then it gets it. That's how slow normal computing works. Brute force one by one, or in parallel sometimes. If you have a huge graphics card and you do some advanced decryption, crack station kind of things, you can do it in parallel, but still it takes a lot of time. But when it comes to Grover's algorithm, right, it takes an approach where it finds it uses search, kind of accelerates the search problems. It's basically you have a huge 1 million passwords with you, and one of the password is the actual password for this application. You have to search it, right? So Grover's algorithm is pretty good in going ahead and searching a huge unstructured database for a right key element. And that's what Grover's algorithm is. And if you look at even Brasser's algorithm, right, it's a bit similar to Shor and as well. It gives you hash functions collisions at the end of the day to crack what is the password. So what is the key? So there are some quantum, in a nutshell, in quantum algorithms, there are some algorithms that can be used to reduce the power or effectiveness of any encryption protocol that is out there. And now we can discuss about how Shor's algorithm is different. So this is the number of digits. It means how big of the key it is and how many operations it takes for a quantum computing powered algorithm versus a traditional classical computing algorithm. So for a quantum computing algorithm, it takes, I mean, less than 10 to the power of 7 or 10 to the power of 8 operations to crack a 300 number of digits, 300-bit kind of a key. Whereas in classical, it takes exponentially way higher actually. So, and even if you ask me a simple mean, right? In theory, I mean, you have to use Shor's algorithm to go ahead and crack some advanced stuff. And if you ask it basic stuff, it's a pointless use of resources and compute to solve a simple problem. You want to kill an ant, just tap it, it will be dying. If you want to, don't use a huge hammer to go ahead and kill it. So the next algorithm is Grover's algorithm. And even Grover's algorithm is out of the box available in a lot of public service cloud providers. So you can just deploy it, and then you should be able to, yeah. So you should just deploy this, and then you can create a circuit. And once you create the circuit, you can always go ahead and keep giving it some values, and it will give out the responses in terms of solving the prime integers and those type of things. And Grover's does the search things. It helps you identifying what is the password or what's the key for in a huge unstructured database. And if you have a quick thought, something like, okay, Setu, you mentioned that there are some very good encryption standards that are out there, and you have also mentioned that there are some quantum computing algorithms that can defeat.
There is a question for you.
Okay. Okay, the role of homomorphic encryption in quantum computing. Okay, Vinod, if you ask me questions in the deck itself, it's very hard, man. I never spoke about homomorphic encryption in the whole thing. So, I mean, I don't know what is the answer for it, but I heard of this one. So if you want to, if you have data and if you want to only encrypt few bits of data, I think that's it, that it is, but I don't know exactly what it is, but I can always take it offline and answer those questions. Yeah, thanks. Okay, cool. So yeah, I mean, you may always have a question like, do we still have strong encryption methods that are out there? And the answer to that is pretty straightforward. Yeah, so we don't have it. The reason why we don't have it is each and every algorithm that is being used as of today can be depleted or can be reduced to its potential using these type of using these type of computational powers like quantum computing. So if we talk about ECC, right? ECC, an algorithm that we have discussed, that it is being used in IoT devices heavily for its amazing speed at which it can encrypt the data and transmit, and the amount of security it provides. So the weakness is basically it again have the elliptic curve discrete logarithm. It uses that. It relies on that mathematical problem, and the quantum Shor algorithm can go ahead and easily solve that logarithm problem to find what is that key, and that makes the ECC algorithm ineffective against computing algorithms like Shor. Yeah, Shor is the major one that is used. If you want to have anything that is to prime numbers or anything like that, I would go with Shor. So the reason why I have been telling this is I don't know much in terms of like how under the hood Shor actually works, how under the hood all this advanced algorithm works. But as a practitioner, right, we can only understand the technologies. You should read like in a very high level. Okay, this is what it is. It can be used to crack it. Okay, that means that thing is being told by these amazing PhD folks and scientists that are out there. And for practitioners, it's all about, okay, they told it and it has been published in NIST. It is pretty standardized. Go with the assumption rather than reinventing the wheel. And then what we do is like we go ahead and start collecting the data and start collecting the encrypted data to go ahead and use these algorithms to crack those encrypted data as well. So you may always ask a question. So Setu, right now, today, my data is in a server and it is encrypted. And hacker has stolen it. And it has AES 256-bit encryption or AES 512-bit encryption on it. Do you think the hacker can use computational power or quantum computing to hack my data? If you ask me that question, my answer would be the hacker will not spend that kind of resources to do it because it's very expensive. but in future it will definitely become cheap. And that is the reason, right? Data is the king always. Data is the king. So we have been scraping a ton of information. Like for example, we have been scraping a ton of public data that is out there, even encrypted, unencrypted in our platform, because we are a threat intelligence platform. We tell how hackers are looking at your organization. We tell what are the threats that outside people are posing to your organization. That's what we care about. So we collect a lot of intelligence from surface web, deep web, and dark web. Sometimes we collect the encrypted stuff, and we need to go ahead and provide the intelligence around how it can be decrypted. So sometimes we run our own algorithms for our premium customers to give the data back. So the question why did I open the tab? Okay. Yeah. So the reason why I wanted to quickly show you this is there is always in history, right? In history, we always believed that Enigma. So Enigma, this is the Enigma machine. So this is an machine that is used by in the World War II. I think it has been used by German folks to come in the U-boats or the submarines. They were using this machine to communicate between multiple places, and they were coordinating huge disruptions across the globe. And this is the mode of communication, encrypted mode of communication. And they were thinking like, okay, it cannot be broken. It cannot be breaken or broken. So, and the researchers from, I think they're British mathematicians, they were able to go ahead and crack the code for Enigma, and they were silently listening to all that information, but they were not respond. They were not they did not expose that, because if they export it, they can always change the algorithm or change the routers, and then they can harden it within a weekend. So they didn't want to do that. So they were sniffing all that information, and then they used it, probability and statistics, and they used all the stuff to win the world or to defeat the Germans. So what were the, again, even if you look at another incident called as Heartbleed. So Heartbleed, this is another bug that came out in past in the SSL TLS implementation. So we all know that we use certificates, TLS certificates, TLS 1.2, 1.3 to secure our data. But at a given point of time, the implementation has been done in 1980s or early 2000s. And the bug has been there for so long. And that same implementation of SSL, the OpenSSL cryptographic library, it is used by so many enterprise organizations, including Google. They were all using this cryptographic library that has been not well maintained, because there are not many open source contributors that are out there. So it has been developed and it is being used, and there's a critical bug in it, and that critical bug made the entire world, made these attackers to read the plain text communications. And this is the same bug that is present in a lot of enterprise VPNs as well. So they have tested it out. They're saying like they tested it on themselves, and they were able to steal the secret keys for the certificates, usernames, password, instant messages, emails, and everything. So the funny part is this bug came out sometime in 2014 or something. But the problem is this bug has been exploited by, yeah. So it has been, it has been exploited by state governments or cross-border intelligence organizations, military intelligence agents for more than a decade. So, because what happened was NSA is National Security Agency of US, and they have a huge set of hackers. They have amazing hackers, and they have hacker exploit kits. Those exploit kits can be used across the globe to monitor cross-border intelligence and whatever it is. They can get a lot of information using those things. So one time, what happened? Some of the other hackers hacked NSA's network, and then they leaked those dumps. And that's when they came to know that NSA had this exploit way before anyone, way before this vulnerability came out public. So they were using this 0-day for way longer, and dump. I think it's NSA dump. Yes, these are the guys. So the hacking group is called as Shadow Brokers, and they exposed NSA's dump, NSA's exploits to in a public GitHub repository. So in that GitHub repository, the heartbleed exploit was there. So it can indicate that even before the vulnerability came out, the NSA or the government has known about it, and they want to silently sniff the entire world as well. I mean, it's not just even in the latest one, even in the Snowden case as well, it has been the same thing. So Snowden is again an NSA hacker. The movie also came out of it. So they were able to have they were able to remotely access other people's webcams even when the laptop is turned off, and this technology has been there in 2003, and it came out like in a late like a decade later. So anything that comes out of intelligence, we can always assume that that technology has been there with military for at least 5 years, 10 years ago. They have been using it. Even the walkie-talkies, they were been using it way before, and then came the cell phones. So the military and those type of organizations, intelligence organizations, they have all these things way before. So the public news right now is DS encryption can be broken, and RSA encryption can be broken, and there are a couple of other algorithms which can be weakened. So that's the public news. So that's the public news, and I will leave it to your assumption what the actual thing behind the scenes would be. So yeah, coming back. So let me, I mean, in the same way, Diffie-Hellman algorithm is used for key exchange. And key exchange, we always, one of the most important thing is like, there are two endpoints, and these two endpoints want to establish secure communication, and they want to exchange the keys as well, right? So even that is based on some mathematical problem. And that mathematical problem can also be solved or bypassed using Shor's algorithm, using the quantum computing quantum algorithms, because they use totally a different logical reasoning kind of a thing to find that solution way faster than the traditional linear computing stuff. The same with RSA as well. So RSA, they use large integers, and those large integers are formed with two prime numbers, and you have to go ahead and, I mean, if you want to crack that RSA, if you want to crack RSA encryption, you have to just find those two prime numbers, and you should be able to crack them or weaken it. So again, even Shor's algorithm can factor the large integers at not exponential time, but in polynomial time. So that can break the RSA encryption. So in the same way, if I mean now the way why I'm taking this in this approach is, so Diffie-Hellman for key exchange is can be broken. RSA for the public key private key cryptography, that can be broken, and AES to store the data at rest can be broken. So in transit is gone, in rest is gone, and in transit also key exchange mechanism is gone. So we can always come to a conclusion like there are vulnerabilities every damn place. So you may always ask me a question, okay, why does it matter? The entire world is on RSA, on those type of things. Why does it matter? I mean, the reason why it matters less as of today is, I mean, for us is, I mean, our data, getting our data at the cost of quantum computers is more of a less care. But this is more of an problem for the government organizations and public service cloud providers like AWS, GCP, Azure, those type of folks. For now, it's big problem for them and less of a problem for us. And any asymmetric algorithm or asymmetric encryption is heavily based on factoring factoring two prime numbers. And any symmetric algorithm is based on only one key will be there in symmetric, right? You have to guess the password. So it's basically searching in a huge password breaches database, which is like, I mean, even if you search like checklist passwords. Okay. So these are some common credentials. I mean, there are like 10 million passwords. There are like 10 million top. Like there are like word lists that are created out there. They're already up there. This is like 10 million on GitHub. So if you go ahead and look at some other private professional services like stuff like this. So CrackStation is another service. You can pay these guys, and they will use heavy computation servers to crack the hashes that you want to crack them. Tomorrow, these guys can also offer quantum computing to go ahead and crack those TLS communications or certificates key that a website uses. So we never know, right? So if you look at the CrackStation's word list, it's 4.2 GB compressed and 15 GB uncompressed. It means 15 GB of a simple passwords that are out there, the combination of passwords. So the passwords are already out there. All you have to do is like use this huge, I mean, this is what these guys are offering. If you go to dark web, they'll have like 45 GB, 60 GB, the paid ones. So the dump is, even you can think like, okay, I have very complex password, it cannot be guessed. I think more or way like partially also it can be broken and then figured out as well. So it's a very serious thing, and it can be only achieved with the help of quantum computing. So it poses a significant threat as well for the organizations out there. And as I mentioned, right, RSA, ECC, and AES, all these three are vulnerable to quantum attacks. Either it can be because of integer factorization, or it can be because of Shor's algorithm and implementation flaws in ECC, or AES is basically searching the password. So based on these things, the limitations, the quantum computers pose significant threats. And the algorithms that we were talking so far, the Shor algorithm, Grover's algorithm, Bassard's algorithm, all these algorithms are straightforward open source out there. So you can always use these things to, I mean, if you already have a huge inventory of breached credentials. So if you go back to this one, right, you may think like, okay, Setu, I do have my data and I'm going ahead and using my data in and storing it in a public cloud. I'm not storing it in a simple way. I'm going ahead and really hardening it, and then I'm storing it using encryption and all the fancy stuff. So bucket, okay, we go to so server side encryption. I'm doing this, and I'm choosing my own private key, and I'm encrypting it. So as of today, right, it's they don't care much for your data as of today because it's very expensive. Tomorrow definitely it will be cheap because I mean, initially when bracket was not there, going ahead and running quantum algorithms was a luxury thing in some research universities and those type of places. But now bracket came and they are having the devices on their end, and we just have to submit our job, and the job will be queued in the reservation pool, and you can always go ahead and create bracket directs as well. So if you look at this, right, no devices, and I think you can create your own. You can just purchase, you can spend more, and you can skip the queue as well to run your algorithm in a quantum computer. So it becomes so cheap right now. It charges you based on how much time the notebook job is running, and it charges you $10 or $100, whatever it is. It's not that expensive compared to having your own quantum computer to run these algorithms right now. So it becomes a bit cheap, and it will become more and more cheaper in future due to the advancements. And at that point of time, what they'll do is like they'll just even today, right, it's mostly available. So you can just search for gray hat warfare. You can just search for gray hat warfare, and this is a website where they go ahead and sell the data that is in like for example RMK. I'll just add RMK over here, and I should be able to see a ton of information that pretty much shows what are the buckets that are out there that are having the RMK fall collection. RMK, I think this is fall collection is what is, guys? I think it's an RMK. Is there any clothier branding over there anyway? So the data is already out there. Even this is encrypted today. In future, they will just mine this data and keep it. And once that cracking thing becomes cheap with the help of quantum computers, then they will go ahead and use this data to decrypt it. So as of today, I think there's a lot of hackers or hacking organizations that are doing mining of encrypted data. Today they can't crack it, but tomorrow the encryption can be broken, and tomorrow they'll definitely crack your data. So that's how it is. Coming back, what are the other threats? So there are a ton of threats. I mean, we have been talking about only the encryption side of threats, but there are man-in-the-middle attack stuff happening. The digital signatures can be forged, and code injections can be done to pretend as a totally different user, because most of the enterprise applications or web applications use JWT tokens. It's also an encryption or cryptography over there. It's not encryption, it's cryptography over there, and that can be broken to go ahead and mimic that a random person is Setu, and they can go ahead and use my banking credentials to log in and transfer a lot of money. So all those things are possible as well, because all these things under the hood uses cryptography, and it can be broken by quantum computing. Intercepting encrypted messages, stealing sensitive data, all this stuff are some of the examples of quantum enabled attacks. So now you may be wondering, are there any solutions that are out there? And those solutions are, any solution, right? So it can be an Iron Man who got all the 5 Infinity Stones and then he'll snap it again. So the solution here is quantum safe cryptography. The good thing is there are bad guys, there are good guys. Personally, I feel always the bad guys are a bit ahead and good guys are always chasing behind. So we do have something called as quantum safe cryptography, and it can also be called as like post quantum cryptography, PQC. And this is standards and those type of things that this NIST, CIS. I mean, there are some industry standard benchmarks that are out there for cybersecurity, just like how ISO is like for manufacturing stuff is there, like the certification. So in the same way, NIST, CIS, PCS, those guys also have the standards. They will publish the standards, and there are some standards coming that came out for quantum safe cryptography, because they don't want the internet privacy to be lost to quantum computing. And if you ask me why, okay, the reason is why is already that you should be clear, you should be already aware of. If not, it would be like me explaining the whole Ramayanam, and then you are talking what's the relationship between Rama and Sita. So yeah, I mean the threat for quantum algorithms is straightforward, and it is just multiple quantum algorithms being used to crack or break the encryption standards or cryptography standards that are out there, and the mission is to protect the critical data. So you can always have a question around like, okay, fine. Now we know that there is something called as post quantum cryptography. What are the different approaches? Lattice is an approach. Basically these are the, because in NIST, right? So they always come up with a problem, and they will let some scientists work together to give some algorithms as a solutions. So RSA is also an encryption standard that came out in 1970s, 1980s. It's just three people to do three PhDs, three scientists together. They built it, and their name is there for how many? More than 3 or 4 decades. The same way Kyber is on these folks. They would like to put their stamp on the global internet. So they are very passionate folks, amazing scientists. When I was in AWS, a couple of my buddies, they wrote the encryption modules for AWS key management service under the hood. So they talk about encryption to me, and researching about all that stuff. Half my hair is gone while working at AWS. Glad I came out of AWS before my rest of the hair is gone. So yeah, I mean, these are some algorithms, and they keep competitions. They have some finalists. The finalists are Kyber, Dithylium, and Falcon. So these are some encryption algorithms that are based on lattices. It's a mathematical problem. I don't know much about lattices, but in a nutshell, it is like what they have explained. What they normally tell it is, it's an infinite kind of a chess square kind of a thing. It expands, and it becomes very hard to guess for a quantum computer through logical reasonings or linear computing through parallel sequential analysis to crack it. So these are some algorithms that came out of lattice-based cryptography, and they are finalists right now. And at the end, recently, like 1 month or 2 months back, they announced what are the final and what are the recommended ones for the entire globe by the NIST. So, I mean, these are 3 things, and they always have multiple different type of approaches for any problem. And there are like code-based cryptography. This is basically, initially they use error correcting codes in a nutshell. What is the meaning of that is error correcting codes have been used for data loss in network packets. So the same approach, error correcting codes have been used to create a code-based cryptography, and it is not targetable for the quantum computing. And there are some examples called Michelle's bike HQC. These are some algorithms that are examples out of code-based cryptography. And there are hash-based cryptography, isogeny-based cryptography. So in respect of time, I'll just move forward quickly. And if you ask me which of the ones that you should be using, always my recommendation is follow the NIST or follow the CAS, those type of folks benchmarks. So in August 2024, recently, NIST has finalized the initial set of post-quantum encryption standards. What are the ones that they recommend for all the big enterprises to use? So security practitioners like me always keep a tab on NIST, always keep a tab on CIS, always keep a tab on CISA. There are like multiple organizations that are out there. We just have to be aware of what are the latest news, latest trends, so that we can implement those latest news and trends based on those recommendations in our organizations to secure. So the practitioners always follow NIST heavily, and the three algorithms that are approved by NIST are I think this is the one which is KIV, and I mean this is majorly they use lattice-based encryption. This is for encryption at rest, basically. So if you want to go ahead and if you have a key and if you want to exchange that key, and that's when you use this algorithm method. So for practitioners, right, we just want to know like, okay, what is that encryption method that NIST suggests to go ahead and use for building a single sign-on application or architecting a single sign-on application or authentication application for the key exchanges. So the solution is MLChem, and the other one is for signing the digital signature. So just to make sure you sign it, right? For example, if you have a file, you can always sign it and then say this is an to check the integrity of things. For that, to make it defendable against the quantum computing, the suggested one is MLDSA. This is also uses the same lattice-based, and this is also lattice-based. And the third one is hash-based. They call it as SLH DSA, and they do the same thing as digital signatures as well here. All the certificate authorities, they have the digital signatures, right? The same way they use the same thing, but with a different problem. They don't want to have the entire world following only one algorithm, and tomorrow a heartbleed kind of a thing comes up and they don't have something to switch. So these are some things that are currently NIST approved. Yeah, and the quick overview of, I mean, these are the descriptions on how those works. The high-level overview of cloud service providers. CSP is just cloud service providers, by the way. So the way how cloud service providers like AWS, Azure, Google Cloud, how they are tackling it is they are not worrying about their customers' data as of today, but they are working in future. So tomorrow future, someone will be able to mine all this stuff and then crack it with the right amount of computation that is out there. And even right, not just CSPs, even if you talk about the hacking community, right, there is something called as Tor, and this is called as the onion routing, and it's like it's a online what is this called as, it's like it gives you a lot of anonymity, and you can always confidently confidently surf the web on also the dark web using Tor, because it doesn't reach out, it doesn't reach the server directly. Instead, it goes to multiple hops. Those are which are like Tor relays. And right now, there are so many government intelligence organizations that are setting up these relays. They are hosting it just to grab that data, the exit node data, and then use it later to decrypt it. There are already, just like how once upon a time Enigma is used by the mathematicians or intelligence organizations to crack the German communications. In the same way, they are using quantum computing as of today to capture the traffic that is going out of Tor in the exit nodes, because these deploy their own nodes, and then they'll capture the traffic, and it's all encrypted. You can't reverse trace it from where it came out, but you want to have access to the data. So they're using some, that's what we got intelligence. So they're like multi-state sponsored hacking groups with like few acres worth of data centers performing some advanced decryption on the encrypted communications on other organizations, military intelligence. So those type of things are happening. And in the same way, the CSPs also care about them a lot, because in CSPs, there is also something called as Gov Cloud. So all this amazing, this is AWS Gov Cloud, then you can always have Azure Gov Cloud, Google Cloud, Gov Cloud. So basically, what is a Gov Cloud is government cloud. So it's a bit more stringent with security and all these things. And Amazon Web Services and these type of organizations do host servers that belongs to governments. So they want to have extra additional protections for them. And even these things are vulnerable as well. So they want to protect against these type of threats. I think the NIST standardization is the option that even they will use because they have to get certified in terms of multiple certification authorities, and those certification authorities will have the NIST standards as the Bible. And sometimes they don't have the knowledge or they don't have the right resources, so they always partner it. So either it is academic research or it can be like quantum computing shared ownership organizations, those type of partnerships they do to help the customers, or they improve their business or improve the security. And if you ask me, like, okay, we do have already data at rest enabled and it is encrypted through AES. How, and this is this is attackable by quantum computing. How can I go ahead and not just do a huge migration of decrypting data and encrypting it back with something else? So it's a huge effort, right? For enterprise organizations, it's some petabytes of data that they have to migrate. So in that kind of a situation, it's always wise to use a combination of traditional cryptographic methods with post-quantum algorithms. And slowly, for example, in AES, if there's one weakness, they'll provide an upgrade or update to it with where the prime number generation can be changed to something else. So those type of migrations happens phase by phase, and gradually the integration of quantum resilient technologies without breaking the infrastructure or breaking the network can be implemented, because you already have TLS 1.3 and now you have to go ahead and upgrade to something else. There can be some outdated servers, there can be some very critical servers that cannot be upgraded, that running on some outdated versions. So it's a huge liability and also a huge work for big organizations. So they have to, they will be coming up with some rollover update kind of plan over a period of time to tackle this quantum computing threats on the encryption side of things. I always love how my professors give me important questions that will be coming in the exam. So this is not the these are, as I always say, these are not the only things that will be coming out. At the same time, there can be a few more coming in from the text as well. But these are the key takeaways. I would always strongly suggest you to go through these things. Just like a good, I always love those professors who gives me like, Setu, this is an important 16-mark question. Please study it. It will come for the surprise test tomorrow morning. And the next day morning, I'll be going out to some other security conference or a hackathon and standing in front of the principal room for the next couple of days outside the college. Anyways, so these are some things that I always love to have, and quick summary. I just put them at the end so that you can go through them and then understand whatever the things that we have discussed so far. And we are 9:36, and I think it's pretty much it. If you have any questions, you can always feel free to ask. And I'm just let me just open the chat. Okay.
Any
We do have
questions?
123 folks in the call, and it's amazing that whatever I've explained went straight into your heads and you don't have any questions. So I can assume that I did a good job, but yeah, you can always ask any questions that you have.
The thing is that it is a pretty higher level, like we are all new to quantum computing, and it's good to see that it is put in practice, at least by demonstrating that AWS bracket. Is there any questions from audience?
And if you have any questions offline, right, later in the point of time, you get any questions. So I'm always available on LinkedIn. You can always, this is my profile. I'll just put in the chat. We can always connect on LinkedIn. On the other side, I'll also put in the chat my email address. Okay, everyone. Okay, send it to everyone.
There are pretty some questions, Setu. You can check the chat.
Yeah. Yeah. So I'll just put my email address.
Yeah.
risk profile. So that's my email address. And just in case if you want to connect. Yeah, just if you want to connect with me on WhatsApp or anything like that, that's my phone number. So right now, I mean, yeah, let me do some advertisement as well. Arun did some advertisement, so let me do some advertisement. So I mean, right now what we're doing is like I'm hiring guys. So we need some solid interns who can be converted into full-time engineers in near future. So we did close a big funding round recently, and that opened up like 10 roles, multiple roles that are available on our website. So if you have any students that you can think of, like these guys are like hardworking and they are like having that logical reasoning kind of things. We don't care about like much programming. We can teach the programming, but if they are solid in terms of not the book folks, but the logical out of the box kind of things that they can always do, please feel free to refer or ask them to submit for the internships that are out there. And that's pretty much it. So let me check the questions that are out there in the chat. So can we use classical crypto analysis in quantum easily? Can we use classical crypto analysis?
There are questions posted before that as well.
Okay. Good. Let me.
Fatima madam has asked like to differentiate the quantum safe and quantum threat.
Okay. Okay. This is so this is basically a question which is like quantum safe and quantum threat differentiate. So, do you want me to explain what is the difference between quantum safe and quantum threat? I mean, I'm just assuming that what are the encryption algorithms that are quantum safe and what are the encryption algorithms that are quantum threat. So quantum threat we have already discussed, and there are some quantum safe algorithms like SHA-256. All those things are not vulnerable because they don't use prime integers and those type of things. Any hashing things are like less vulnerable for quantum targets. That's the answer for Fatima. And we do have one question from Nitya. So protocol to be used for security and error correction as well as detection. Okay. Actually, protocol to be used for security and error connection. No idea what the question is. Okay. Which protocol can be used? I mean, I don't know how to read this, but protocol to be used for security and error correction as well as detection. No idea, Nitya, no idea. Okay. There is, can we use classical crypto algorithm in quantum easily? Crypto algorithm. Okay. In quantum, you use quantum algorithms, and you can always run things like that take the reasoning as a factor and solves any given problem very quickly. So anything that's a little more logical reasoning and those type of things, you can use quantum as an underlying compute for it. So I don't know what is the meaning of classical crypto algorithm. And okay, interesting information. That's it. Yep.
Classical crypto algorithm, they are meaning that without quantum embedded into it.
Oh, okay.
Yeah.
So the question is, can we use like normal algorithms on a quantum computer kind of a thing, right? I think these are a bit different. No, it's not. I have never seen any normal algorithms or normal notebooks that do not require quantum computing being used. I mean, I have seen the normal algorithms. If just in case of speed, if you want to speed, like okay, this is a problem that I have, and this is the algorithm that I have for the problem, and I want to go ahead and run it on a quantum computer because it can quantum computer can do it at a faster pace. I would always recommend using some kind of T3X large and those type of memory intensive, GPU intensive kind of machines. you can also rent supercomputers as well. So on those type of CPU intensive kind of stuff for the normal stuff. And when it comes to reasoning and other things, running the Jupyter notebooks that solves some kind of fancy logical problems. Even the AGIs, they are running it on quantum computing. So for those type of things, you can always use quantum computers. And cool. I think that's pretty much it. So perfect. I think it's 9:40. Good. Thank you so much, guys. Thank you so much for your time. And any questions that you may have, you can always reach out to me.
There is another one question, like I'm asking about BB84 and B92, their difference. What is that?
Out of question.
Okay, okay.
If you ask anything that I should be able to answer. But anyways, I'll just
Yeah, they are all protocols, it seems.
okay. They are like some important quantum key distribution protocols. Okay. So I don't know. So if you ask, so this is basically an out of portion kind of a thing. I never follow those protocols, and I'm just googling what those are, and then it's like it says that those are some quantum key distribution protocols that came out in 1980s. So okay, pretty solid. Perfect. Thanks. Anything else, by the way, Subha?
I think we can wind up the session. Yeah, like
Perfect.
I would like to thank Setu for having the fantastic session on impact of quantum computing on modern cryptography protocols, particularly in the context of cloud platform. Yes, with the demonstration of AWS bracket, we found that it is in use. This quantum computing is in practical use. And many of us are very new to this quantum. So the first session was about the introduction to quantum. It was like a baby step, and what you were talking is like the high level, the application level. And you really broke down the complex topics into a simple one. And we had a basic info about that ecliptic curve cryptography, AES, RSA, and finite field Diffie-Hellman algorithms as well. And to add a note, starting from Enigma to that Tor onion routing, yes, the quantum enabled attacks and the post quantum cryptography, everything we a little bit we got it as an overview. We need to found it again by working on such kind of applications. So lastly, it would be very great to have you for this wonderful session. Thank you, Setu. Thank you so much. So on behalf of all the participants, I would thank you for joining us today.
Yeah, perfect. Thank you so much, everyone. Thank you so much for your time, and totally appreciate being patient with me. Thanks.
Hope to have you again. Thank you. Yeah. Yes. I will request all the participants, please enter your registration of attendance for both the sessions separately. So from tomorrow onwards, it will be randomly posted, and so please keep an eye on it. For session 1 separate and session 2 separate.